Can try the audio.
Okay, hello.
Okay.
Can you hear me?
Good.
Okay. Yeah, I think I speak loud enough. I'm not sure if I need that, but
The Zoom we can do it.
oh, but the Zoom is a separate one. Is it okay if I don't use that and I speak? If I speak like that, is it good? Because I tend to shout, so this is gonna be unpleasant, I think. Okay. Just no, but I think even people in the back is gonna be okay. Well,
Only the Zoom.
yeah, the Zoom is here, so as long as people can hear me in the Zoom. Okay. Or if you need it, let me know and I can swap. Can we start?
Okay, thank you for coming here. So we continue with let's go to the conversation.
Okay, yeah. So thank you for coming for the second lecture. So let me start by giving you a brief recap of what we did last time. So last lecture had the goal of essentially conveying, I guess, like three messages. So the first message is that statistical physics is the study of high-dimensional probability. So any problem that can be cast in the language of high-dimensional probability in principle can be treated with a statistical physics approach. One classical example is, physics, many body physics, and that's where physicists start studying high-dimensional probability. But there are many other high-dimensional probability problems in the wild. And yesterday we saw one example, which is like inference problems, or sometimes also called inverse problems, where you have a signal is transmitted through a channel, the statistician observe the corrupted version of the signal, and the goal is to ask how much information do you need in order to infer back or to invert this problem. And here, the fact that it's hard is because the problem is not bijective. So here, by noising and perhaps also compressing, you lose information. So it's not obvious that you can actually invert perfectly this. In some cases, yes, some cases, no. And the goal is to understand, how much information actually you need to invert. So that was the first message. The second message was a historical message. So I wanted to share with you a little bit of the history of this field. And we went over it and we saw some examples of early interactions between computer science and machine learning. And so finally, towards the end of the lecture, we looked at let's say the third part of the lecture, which was concretely seeing how ideas from statistical physics can be useful in computer science. And we focus on a particular context, which was the problem of typical case complexity. So let me try to remind you what this means. So in computer science, one of the most important questions is, can you solve a given problem with a computer? And if you try to mathematically define that, essentially you get to the problem of how hard it is to compute something. There's a classical complexity theory, which it's called, like, I guess you all know, like the conjecture, like P is equals to NP or not. And this relies on the classical notion of complexity, which is a worst case notion, which essentially proves that, no possible instance of the problem can be solved in polynomial time, with an algorithm. So the game is essentially the following. You give me an algorithm, and I can cook up a problem which is as hard as possible for your algorithm. And if I can beat your algorithm, then your algorithm is not good. But the game is this. You give me the algorithm, and I give you the worst possible instance of the problem that is going to be as bad as possible for your algorithm. That's not the way, science and actually the way we work with computers, right? The way we work with computers is that you give me the data, and I do an algorithm for this data. So it's not worst case. Actually, in practice, we are interested in how algorithms behave for typical data. So data that you find out there in nature, right? Like photos of cats and dogs and, I don't know, stock data. So this worst case complexity theory is very nice because it gives you very strong guarantees, but it doesn't manage to capture part of actually the practice of computer science, which is, even though I can prove some problems are NP hard, so they cannot be solved efficiently. So one classical example is KSAT. if you give me ksat, we take a random instance of ksat and we try to solve it using a neural network or any kind of like solver that you like. Sometimes you can solve efficiently, even though, it's NP hard in the worst case. So computer scientists have been spending a lot of time thinking, okay, if worst case is not, let's say, a good notion to describe what is going on in real life, let's try to cook up theories of typical case complexity. Now, that's very hard because what is a typical instance of a problem, right? Try to think about, like, in the context, maybe for ksat it's a bit more abstract, but try to think in machine learning, what is a typical distribution of data? Then you get to the problem, okay, I need to model the distribution of photos of cats and dogs. What is this distribution? Does it even exist, a distribution over, let's say, human language, like of English, of cats and dogs? So going towards reality, you also get into a modeling problem that is hard. And defining what is typical is not an easy problem. So there are different notions of typical case complexity in computer science. So one of them comes from physics. And it is the notion that we discussed yesterday, which relates computational complexity to metastability. Let me remind you, metastability is this phenomena that because of the competition between energy and entropy, when you look at the landscape of the problem, you might have minima, which are not global minima in your free entropy, in your free energy landscape. And the fact that there is a barrier and this barrier grows with the size of the system means that local algorithms, when navigating this landscape, will not manage to escape, even if you add noise. So meaning that there are local minima which are stable in the thermodynamic limit or high dimensional limit. So this notion of metastability, which is very important in physics, translates to a notion of computational hardness in the typical case. And physicists have been pushing for this notion in computer science. As I told you towards the end of the lecture, there is still no consensus of what is a good notion. There are some proofs of equivalences for some problems, but it's problem specific. And physicists have been giving bold conjectures saying that that's the notion of computational complexity. Computer scientists are not always on the same page, but it is one of the notions in one of the serious notions of computational complexity. So we illustrated this in a specific context, the context of these inverse problems, where we discussed a very specific one, which is like generalized linear estimation, where we want to invert this problem for a channel where the observations is related to the signal by some linear projections. And here, I'm going to be assuming that these projections are like random projections. So for this problem, we can write down the posterior distribution. It is a high dimensional probability distribution. Well, let's apply statistical physics to it. We apply the notions that the tools we have for statistical physics, more specifically the replica method, to characterize this. Because the projections are random, this allows us to use a mean field approximation. And in the limit, this approximation gives us a large deviation principle for this measure. And this large deviation principle is given by this formula. And we discuss how this translates into this, let's say, diagram for, let me put the full thing because we discussed this in detail yesterday. In this diagram that shows like how the mean square error behaves as a function of the sample complexity. So sample complexity, I remind you, is the amount of information you have, because the larger the alpha, the more data you have per unit of dimension. And we saw how the metastability, appearance of metastability on the large deviation potential is related to the fact that there exists a phase, which is called a hard phase, where I claim local algorithms such as gradient descent or stochastic gradient descent for trying to invert this problem will not work, even though information theoretically, you should be able to recover the signal. And when I say information theoretically, what you should think always in your mind is, if I had like infinite computational power and I could actually run, like Monte Carlo for the posterior distribution for exponential time, I would be able to sample, compute the mean, and then I would be able to achieve recovery at alpha equals to 1. But this would cost exponentially, right? Exponential because the measure is high dimensional and because there is this metastability. So you need to jump this barrier. So the conjecture is that in this region, even though you have information, enough information in the data to recover the signal, you cannot do it computationally in linear time or polynomial time. So this is what is called a hard phase. And so this is one example, but this type of diagrams is everywhere in this field of typical case complexity. Essentially, is a field that has evolved since the 2000s with physicists and computer science working together, and there are many, many problems where you can derive exactly the same pictures. So even though I'm showing you this for one example, this connection and this idea of metastability implying computational hardness is very general. And you take your favorite problem in computer science, as long as you define a typical instance of the problem which is random and is nice enough, one should be able to derive some kind of mean field picture that leads to something like that. So that's what I wanted to convey. Is one example and is one early example of this interaction between physics and computer science. Is very successful. And so in the end of the lecture, we discussed this. We could go on the 2 other lectures just discussing other instances of that. And so Leticia yesterday hinted if I was going to do some landscape computation using statistical physics. So I could, but I'm going to do something simpler. Okay, simpler and more complicated in some sense, because from now I'm going to leave the helm of theoretical computer science and I'm going to get towards machine learning. Now, machine learning is a harder problem in some sense. So what we can say is usually using simpler models. So the content that I'm going to be touching is simpler from the statistical physics perspective, but I'm going to try to go slowly because I'm not sure if all of you are familiar with the notions of machine learning, so I'm going to try to define things precisely, and then you interrupt me if you need to discuss something more detailed. The last thing I would like to say before leaving this is that this notion of hardness, I'm making very general claims, right? I'm saying no local polynomial time algorithm can recover the signal in this region. You might ask me, okay, you are making this connection between local algorithms which act on the parameter space and some sort of local algorithm on the free entropy or large deviation or free energy here because I'm minimizing, so minus sign. I tend to mix all these things, so try to have the mental flexibility to add a minus sign every time I go from free entropy to free energy. But what is the connection between local algorithms in let's say in the parameter space to local algorithms on this landscape? It's not obvious that if I do gradient descent here, I'm going to be doing gradient descent here, right? And it's actually not true. So there is one algorithm that statistical physicists have developed based on ideas that come from spin glass physics and disordered systems, and more particular, the TAP equations. And this algorithm makes this connection very precisely. So in other words, it's an algorithm that is minimizing somehow something related to the distribution. And when you go to the parameter, so when you go to the summary statistics space, this algorithm is precisely going down this landscape. Okay, so I'm not going to spend a lot of time on this, but I'd like to flesh out because just to give you an idea of what are the different directions you can take if you want to work in this field. So this algorithm is called approximate message passing. It's also a big research topic. And let me just give you a little bit of intuition of what it is. So if we look at this specific linear estimation problem, essentially there are 2 steps. You can see it in 2 steps. One is that I have the observation that is related to the projection through some likelihood that adds noise. And then I can think that if I can invert this one-dimensional problem, right, because this is y is sampled from P of y given z, and z is one projection. So, and things are IID of the projection. So this is essentially, you need to denoise, like you need to invert one-dimensional problem here. Then once you learn the projection from the observation, now you need to learn the signal from the projection. And that's the d-dimensional problem, but it's a linear problem. So you can think of this problem as composed as these two sub-problems. And approximate message passing is exactly going to leverage this. So it's an algorithm that tries to first estimate the projection from the observation, and then to learn the signal from the projection. And it does this in an iterative way. So you start with a guess. You start with a guess of a W, then you plug it here, and then you try to self-consistently infer Z. Then in the next step, you try to infer another estimation of W from the Z. Then you plug it back here, and then another, and you go on, like in an iterative way. So I'm going to just show you the algorithm. It's not intuitive. I'm not going to discuss it, so don't bother like paying a lot of attention to this. But essentially, this algorithm is essentially implementing this idea. And just to give you some facts about this algorithm and why it has caught up in computer science and why it's a very popular like research direction, is that this algorithm implements this idea, and in some notion, it is the optimal algorithm to solve this problem. So as long as you have the information about the likelihood and the prior of the signal, this algorithm is going to be the optimal algorithm among all algorithms that run in linear time. So it's an algorithm that essentially the complexity is linear in the dimension of the problem. So it's efficient because linear is good. You know, when I say polynomial, among all the polynomial algorithms, the most efficient ones are the linear ones. That the number of iterations, like as you make one iteration, you just pay the price of storing like a matrix multiplication, because you're just like doing this operation every time you are trying to infer. And it is the optimal algorithm among these first order methods. So one way of seeing this is that by studying this algorithm, since you have this optimality, you can derive what are like lower bounds for solving the problem, computational lower bounds. Because since it's the optimal algorithm, any other algorithm which is polynomial is going to do equal or worse than that. So by knowing what this algorithm does, you can essentially lower bound what is the minimum amount of information you need to solve the problem computationally. So, okay, so if you are interested in that, come chat with me. I'm happy to discuss in more detail approximate message passing. But it is an algorithm that comes from ideas of statistical physics, essentially trying to implement this notion that I would like an algorithm that is doing gradient descent on the space of the summary statistics. So, okay, so just to summarize, that's what I started the lecture today, like summarizing what we discussed last time. And let's go to the second part of the lecture, which is going towards neural networks. So moving a little bit from theoretical computer science to machine learning. And so here, there are two things that I would like to discuss. Probably today is going to be mostly about that, and then we're going to move towards this, is that we would like to understand why neural networks work. And this is a hard problem because neural networks are complex. They are very non-universal. So there are many architectures for many different tasks. The data is not universal as well. So each task has a different data. We need to model the data distribution because as I was trying to motivate to you, we don't want to have worst case guarantees. We want to have like typical case guarantees. And I'm going to come back to that why worst case guarantees are not good for machine learning. And so we need to start very humble when you go to do machine learning theory. We need to go slowly, make strong assumptions, and try to build up from that. But I guess all of you are going to be happy with that if you are physicists, because that's exactly how we deal with physics, right? Like the Ising model is not a model of a magnet, right? I cannot build a magnet from the Ising model, but I can understand the physics from the Ising model, and then maybe someone in the engineering department is going to do the job of building the magnet. So here we are not aiming at telling you how to build your next neural network, which is going to be state of the art. We're trying to capture some, let's say, universality, some universal phenomena from neural networks, which is descriptive. So we are going to start essentially by studying a class of neural networks, which are neural networks at initialization. So you're not you're not actually training the neural network. You're just looking at neural network like with random, like kind of a random network. So that's the step number one. And as you're going to see, this is already not simple. Then, of course, what we like to understand really is what happens when you train your neural network, because one of the reasons neural networks are so great is because they adapt to the data during the training. So the weights change, the weights correlate to the data, and you can see that neural network is learning a representation of the data, which is adapted. And in this representation, it's easy to solve the problem. So you can see a neural network essentially as learning a good representation where things are easy to solve in this basis, like learning an adapted basis. And how this happens during training is what we call feature learning. And we do have some results which are very recent, like I would say 2 years ago, which is about how to study feature learning using tools of statistical physics. So that's, like I say, the culmination of everything, but you have to bear with me. We're going to start simple because things are hard. They are not hard in the sense of statistical physics that have very complex and deep ideas, okay? Actually, the toolbox is going to be very basic from the point of view of statistical physics. There is not going to be replica symmetry breaking. There is not going to be dynamical mean field theory for now. I mean, we could go this direction, okay? But so things are going to be simple in this sense. But the messages we're going to be able to learn from it are going to be important lessons for machine learning. So let's start with this part, which is about machine learning. So I go back to Bryman's paper. By the way, yesterday I discussed this, but if you haven't read this, like it's like a 5-page paper, I really recommend, because it's a great like reflection piece about machine learning and about what does it mean to do theory of machine learning. So the two first questions that Bryman posed in this paper are essentially questions that we don't understand and that we'd like to understand, which is why, when you overparameterize the neural network, you don't overfit the data. When he says overfitting, means that you don't pay a price in terms of performance. We're going to go back to defining what this means precisely. And the second point is like, what is the effective number of parameters on the network that you need to learn a certain task? So we are going to try to address these questions in the context of supervised learning. So machine learning is composed of different frameworks. There is reinforcement learning, there is unsupervised learning, there is self-supervised learning. And let's say that the machine learning 101 is supervised learning. So we're going to start again, for the sake of simplicity, with the simple things. We have data. Data come in pairs of X and Y. And I'm always going to be assuming here that X is a vector in RD, is an Euclidean vector in RD, and Y is a label which can be in a subset of R. So if Y is a discrete thing, a discrete object, we are doing classification. If Y is a real number, like a continuous real number, we are doing regression. And I'm going to be assuming that this data has been independently sampled, so IID, from some distribution, joint distribution over X and Y. Now, I already said two things here that should bother you. So the first one, that the data is an Euclidean vector. You can always do that. You have your data, your data comes in some data structure in your computer, can be a pandas data frame, can be an Excel spreadsheet. You can always make it a vector by linearizing, like vectorizing it, like torch.vec, like something like that, or flatten. But real data is not usually coming with Euclidean geometry, meaning that computing distances in the Euclidean geometry does not necessarily imply a notion of similarity between data points. So if you have a table, for example, if you compute the Euclidean distance between two tables, that's not necessarily meaningful. Or you have two pictures of cats and you compute the Euclidean distance between the pixels of the picture, not necessarily you're going to get like a similarity notion that is good. So when I vectorize brutally my data, I'm losing some information about the geometry, which could be important. Okay, so that's a disclaimer. And part of the research goes into this direction, trying to model geometry of the data. But for the sake of simplicity, we're going to be doing as all textbooks in machine learning do without discussing that. You open data, are vectors, and IID. Yes.
Can you say again why you single out the Y?
Why you have single out the Y? Because we are studying supervised learning. So essentially, this structure where you have like pairs, it's describes a subset of problems, which are problems where the labels are given to you. This is not necessarily always the case. And if this is not the case, you have to think about the problem differently. But these are different frameworks to study the problem. Let's say that people gave you photos and labels of the photos, like cats, like photos of cats and cat, dog, cat, dog. Yes?
You just mentioned something that I know from our realized this week. Actually, one of the problem that we have is data is graphs.
Yeah?
Then we want to vectorize it. So we are not even starting to do machine learning, just
Yeah.
thinking how to find an embedding into a vector space.
Yeah.
But I was thinking this was very particular with graphs, yeah. But then this should be done in many kind of data.
Yes. That's absolutely true. It's like, so when we think about like more generally, like maybe the subject of, I don't know how to call this, but let's say like, let's put under the name AI. I don't like so much this, but let's think about AI like as the field where you gather all the different subjects that concern like learning from data. So there is one part of that subject, which is data science, which is someone is going to get some data, do some processing on the data, and prepare it for machine learning. Then traditionally, the way machine learning is thought is that we receive the data come in some format, and we usually don't change it, and we find what is a good method to fit this data. And so usually we are thinking this already came in this format, and this format is meaningful. But the data science aspect is very important because if you ask actually people that do it in practice, they will tell you that most of the gains you can get is by properly pre-processing your data. So cleaning, putting in a format which is a good what you describe is an embedding. And finding a good embedding for your data is a problem per se. Graphs is one example, but tables is another example. Like pictures should be also an example, right? Like what is the meaningful like geometry for pictures? So this is everywhere. The problem you're describing is everywhere. And it's a major simplification when we say it's a Euclidean vector. And then we use tools from linear algebra to do what I'm going to do next. And the second major thing that should ring a bell to you, I want to flash, although again, I'm not going to address, is that is IID from some distribution, okay? So some things are close to BIID, some things are not close to BIID. So for example, you take some types of data like stock prices are non-stationary. So you cannot say that each sample of this sequence of prices of stock comes IID from the same distribution. That's essentially you are destroying the time correlation in the problem. Other way that things could be non-IID is that you might be training your network on some data set that comes from some distribution, and you might be testing it in some new data. And it's not obvious that the distribution of these two data sets is the same. So this is what's called distribution shift, and is also like a major problem in machine learning to study. It's like a research question, like to what extent distribution shift can mess up with what I'm going to tell you next. Okay, so this line is everywhere in textbooks, but you should always have like on the back of your mind that it's not obvious that these assumptions are natural. Okay, but let's assume these things. So what is the goal of supervised learning is that I would like to find a function that goes from X to Y. Okay, you give me a new picture and I give you whether it's a cat or a dog. So it's a function, goes from RD to R. And this function usually I like to find from the data. Now, I want to find a function that is good at fitting the data. So now we have to bear with the question of what is good to fit the data. So here I'm going to give you one function. So this function is a function from R to R, RD to R. It takes an X. It checks if this X is in your data set. And if the X is in the data set, it returns you the label. Otherwise, it gives you 0. Okay? So is this function a good function or not? Like, are you satisfied by this function solve the problem that we started with? Well, you just need to linearly check over the data, right? And sometimes, I mean, by doing gradient descent, you also need to compute the gradient over the full data set. So it's not too bad in terms of computational efficiency. But
it will overfit the data, but it will predict everything that is in the data.
Yeah.
You can't say anything about anything that you haven't.
Exactly. So this function, I would say in my language, this function is not learning. This function is memorizing. And so here comes the first important notion in machine learning, is that memorization is not learning. Okay. So let's try to define what this means precisely. Is that I don't want something which predicts perfectly on the data set. I want something that predicts on new samples from the distribution, which are not necessarily on the data set. So when I define what learning is, the way I deal with this sentence, I need to do learning well. I want something that learns good. What I mean is the following, is that I introduce some cost function. This is going to be what we call loss function. The loss function is going to take you a label and a prediction and gives you a real number that's typically positive. So if this real number is large, you are not doing well in the prediction. If the real number is close to 0, you are doing well. And then here comes the key notion, which is what we call the generalization error or population risk. In statistics, typically population risk. I'm going to swap these two notions. So test error, generalization error, population risk, I'm going to use this interchangeably. And what we really mean by learning is that we want to minimize the expectation over the loss function. And this expectation is going to essentially convey this idea that I want to do well on the distribution, not on the data, not on the data set. So this function, that is the memorization function, is going to be good on the data, but on expectation is not going to be good. Actually, with high probability, it's just going to be giving you like the maximal error. Okay. Now I know what I want. I want to minimize the generalization error, right? When I do supervised learning. However, there are some challenges. So the two challenges are, the first one is that this quantity is defined by an expectation over the data distribution. So what is the data distribution of cats and dogs, of pictures of cats and dogs? We don't know. So you are minimizing something that you cannot compute and you don't have access to. So this is a problem. Second problem is that minimize. So, well, for physicists, maybe this is a meaningful statement, but if you are a computer scientist, minimizing over the space of functions. So think about like opening your laptop and how do you parameterize the space of functions? Like how do you compute over the space of functions? So this is you cannot do it, right? In a computer, you have like bits and you need something which is parametric, not something which is, let's say, over the space of all possible functions in RD. So the way people solve the first problem is that they say, instead of minimizing over the population risk, the expectation, they minimize over the loss function on the training data. Okay? And that's what we call the training error or the empirical risk. So why they do this? Well, the logic is simple, is that by the law of large numbers, as n goes to infinity, this converges to the expectation because it's IID. Okay? If there was distribution shift, that would not be the case. But because data is IID, this converges to this pointwise, which means that if n is large enough, then this is a good approximation of that. However, this is usually not the case. Usually you don't have infinite data. So here we solve the problem, which is now we know what to minimize because we have the data, so we can, this is meaningful to minimize over this. But we are not minimizing over what we want. We changed the objective. And it's not clear that a minimizer of this is going to be good at generalization. And actually, by the way, the memorization function is a global minimum of this. So we solved the problem, but we didn't solve the problem, okay? but that's how it is. That's what's called empirical risk minimization, and that's the main framework in machine learning to solve supervised learning. People usually run gradient descent here. Now, the second problem is a little bit tricky as well. How to minimize over the space of functions. So here, what people do is that they say, okay, the space of functions is too big. Instead of minimizing over this space, let's take a subspace. So here is the space of functions from Rd, the space of all f from Rd to R. They say that's a very complex space, so let's take a subspace here. Okay, that's what we call a hypothesis class in machine learning, or more, let's say in statistical learning theory jargon, is the subspace of functions. And the way you choose this is that you choose it in a way that is a parametric space, meaning that to take a function inside this space, let's say you can parameterize by some parameter theta, which is a Euclidean vector. So theta is in a space, let's say Rp. So in the end, like I can say that H is the space of functions f of theta from Rd to R, such that theta is in Rp. So that's a subspace, and it's kind of solves my problem, because now to optimize over the space of these functions, parametric functions, I just need to optimize over the parameters, because the parameters cover the hypothesis. And by optimization in Euclidean space, I know how to do. I do gradient descent on theta. So now I'm happy. I know what to do. I have mapped my problem of learning to the problem of optimization. So I need to optimize the empirical risk over the parameters of the hypothesis that I chose. So let's think about some examples of hypothesis class. So let me give you one example, like very simple hypothesis. So the space of functions f of theta, which are linear, theta transpose x, maybe some bias. That's one subspace of functions in Rd. And here, this motivates a very important notion, which is this hypothesis is limited, right? It can only fit linear functions with this hypothesis. So by introducing a hypothesis, which is a selection of a subspace, I'm introducing a bias. So this bias is what is called inductive bias. And this is the bias introduced by the choice of class that you're optimizing. In other words, the choice of architecture. Okay? And one of the major problems in machine learning is to understand the relationship between the choice of architecture and the inductive bias of the hypothesis class. So what kind of functions can I fit with this? Here is very simple, linear functions. So you can think about another example, is like two-layer neural networks. So like, for example, I can select sum from J from 1 to P of Aj, sigma of Wj transpose X. So this is another class of functions. This is what we call a two-layer neural network. And this as well spans a subspace. It's a bit richer because now I can fit a linear combination of nonlinear functions. But it's not so clear what is the inductive bias of this class, right? What can I fit with this? And so on. So the hypothesis is the choice of the statistician. It's your choice. It's part of the definition of the problem. It's like the algorithm. It's part of the definition of the problem. Okay. Is this clear, this notion? Okay, great. Yeah?
So I was confusing why it's layered neural network, because it seems like there's only one set of neurons, right? So what is a one-layer?
It's a perceptron.
Okay, just one perceptron.
I think this is a question of language. So some people call this a one hidden layer network or a two layer because you count the data, like the input as a layer.
Data.
Yeah. Well, yeah, that's language. So, and then a three layer would be adding like one more, but you could also call it two hidden layer neural network and so on.
Scientists should love to index from 0.
Yeah, you should tell them, like, but you know, machine learners are not computer scientists though. Need to be careful. Okay, Good. So you're just formalizing some things that probably you guys know if you have done from sklearn import like something, right? You're choosing a hypothesis when you do that. Okay, so let's take an example. So when we want to learn, and we want to learn efficiently, and we want to learn as well as possible, we want to minimize the generalization error. A question that arises is, okay, what is the best possible achievable risk? Like, what is the best possible achievable generalization error for my problem? So this defines what is called the base risk. So here I'm doing one example. It's going to depend both on the data distribution and on the loss function. So let's take one example. Let's take the square loss function, which is usually a good choice of loss function for regression problems. So we take the square loss, and then we define the base. So that's not the base risk. Sorry. So that's the base predictor, not the base risk, because the risk is going to be the risk achieved by this predictor. So that's the base predictor or function. So that's the best possible function in terms of generalization error, impossible generalization error. And if you compute the minimum of this, you see that this is given by the conditional expectation of y given x. So if you had the data distribution and you choose a loss function, you could compute what is the best possible generalization error. And this is going to be a benchmark. So here, this introduces a notion, which is a very important notion for regression, which is called the bias variance decomposition, and is the following. So let's compute what is the risk of a given predictor. So a given predictor is a given choice of theta. That it might be the theta that you get after running gradient descent, minus the best possible achievable risk. So this is what is called the excess risk. So that's how much you are doing in respect to the best possible. You cannot do better than this by definition. So if you open up the definition with this loss function, is f star minus f of x and theta. So I can essentially rewrite this, and this is a simple exercise just doing the maths. I can rewrite this in terms of the expectation over two things, so the bias and the variance. So the bias is the difference between the best possible predictor. So the best possible predictor is the argmin, minus the average of my predictor over the data. So here, essentially, I have a predictor. The predictor is a random function, and I take the average because the data is random. So the predictor is a random function. So I take the average with respect to the data. So on average, how far I am from the best one. That's what we call the bias, or the bias square, but people typically just call bias. And what is the variance? So the variance is how much I'm paying my predictor with respect to its average. Okay. So the mental picture that you should have is the following. So let's say that I have some two-dimensional problem, and I have some data. It's noisy. And then you fit, let's say that the best possible function to fit is what is the base predictor, is this one. So that's the one that generated the data. So that's f star of x. So that's y, that's x, that's f star of x, and the data is something like f star plus noise. So let's say that your predictor is going to be given by this. So you're taking the average over the noise of your predictor, and you're seeing how far it is from the true one, that's the bias. And then the variance is how far your is with respect to the average over all possible predictors with different noises of this distribution. So that's why it's a variance. It's really a variance over the noise. So you want to minimize the error, you want to have as low bias and as low variance as possible. Yep.
Have any change the loss function to another kind of function, because here you have a square.
Yeah.
In this expression, be the same, or will you have always the excess risk at the sum of the bias and the variance? But
No.
Or will it depend on the function?
No. This is specific to the square loss, this decomposition. So you can always define a similar decomposition, what we call the, let's say, estimation error versus approximation error. But it is slightly different from that. So the behavior, the phenomenology is similar, but this decomposition, as you pointed out correctly, depends on the fact that you have the square loss. So when you take the average of the cross term, you cancel. So you really have this decomposition in terms of the sum of two squares. So this brings me to the notion of bias variance trade-off, which is the following. So if you want to minimize the total generalization, the excess risk, you want to have as low bias and as low variance as possible. Now, the bias is how far you are from the true function, and the variance, it is how much noise you're fitting, right? Because that's the variance of the predictor. So note that this is independently of the base predictor. This is dependently of F star. It just depends on your predictor. And this depends on the true, not true, but the best possible predictor in error. So in practice, I would plot the test error or the excess risk as a function of the complexity of my hypothesis class. So what is the complexity? It will depend on the hypothesis, but you can think as the size of the hypothesis with respect to the whole space. That's the complexity. You can think as the size of P, for example, because the larger the P, the more I can approximate, the more parameters I have, the better I'm doing. Now, if you start increasing the complexity, your function is going to be more and more expressive, which means that it's going to be able to fit more and more noise, right? So here in my example, I'm doing a linear fit. So I'm just picking a linear function. So this has low variance, right? Because I don't manage to fit the noise with a linear function. This noise is not linear. So I'm not managing to find a line that passes through all the points. But if I would take like a polynomial fit and very high degree polynomial, I could fit in principle. So I was using green for fitting. I could fit something like this, like a very oscillatory function, right? And pick all the noise. But then I would have a very high variance because I'm fitting the noise and not F star. So we like to think that the variance increases as the complexity of the class increases. However, the bias is the opposite, because the more expressivity I have, the more likely I'm going to be able to fit the best possible function. Of course, if the best possible function is linear, and I take linear, that's good. But usually the best possible function can be very nonlinear, and then the more complexity we add, the more likely we're going to fit the best possible function. So this is what statisticians call the bias variance trade-off, and tells you that when you are doing a fitting and you're choosing a hypothesis, you should choose a hypothesis which is complex enough to have low bias, but not too much, because then you fit the noise. So you have a sweet spot in the middle. So let me show you an example. So here I have a true function, which is a F star. So sometimes, by the way, F star, the base predictor in physics, is called a teacher. Okay, is the function that generated the data. It is the best possible achievable function in the problem in terms of generalization. So we have a teacher, which here is a sinusoidal function, right? So that's the target function, the base predictor, or the teacher. Then I'm trying to fit this data with a two-layer neural network composed of ReLU activation. So I take ReLU here. So this is a piecewise linear function. And here I have three neurons. I have one neuron here that gives this piece, one neuron here, and one neuron here. And I'm just doing empirical risk minimization on the square loss over the data generated by this sinusoidal. So as you can see, because I have only three pieces, I don't manage to fit the oscillatory behavior of the sign. So I have what I'm having high bias and low variance. On the other hand, if I take a piecewise linear function with many, many neurons, what is going to happen is that I'm going to fit all the noise. And I'm also, I'm going to deviate from the true function by picking the noise. And so I'm going to have high variance but low bias. And the sweet spot, which has balancing bias and variance, is something like here. That's 1, 2, 3, 4, 5 neurons. So this is what statisticians call bias variance trade-off, and it's something that you learn when you do stats quite early on when you're doing polynomial fitting. And here I'm doing this with neural networks. Is this clear? Okay, great. However, this is very nice, but that's how the same picture here looks like for a neural network. So here I'm showing you experimental data. So this is a plot from a paper by the group of Mathieu Viard and his students, so Mario Geiger et al., that did exactly this experiment with a big neural network. So this is what? This is a 5 layers, fully connected, and no regularization. And so here he put the number of neurons as an approximation of the number of data of parameters. And here he's increasing the number of neurons. And he's doing this on a real data set. So that's the kind of something related to MNIST. And so what he's showing is that, well, in the beginning, we do have this trade-off. So when you have few parameters, you have high error, so high generalization error. It goes down. And then, okay, you know, I expect that. The more parameters I put, the less bias, the more variance. And then as I keep increasing, I go up in variance. So that's exactly this U-shaped curve I showed you. However, at some point, I start going down again as you keep increasing the network. And that's crazy. Okay? That's crazy. If what I showed you here, it's reasonable and intuitive, that's very non-intuitive why this is happening. Yeah? That's exactly the first question. Yeah, yeah. Thank you for reminding. Yeah, that's exactly the first question posed by Bryman. Why does heavily overparameterized neural networks don't overfit the data? So why you are not getting high risk, high generalization error, even though you have very, very many parameters? And so here's the second example by other groups, so Nakiran et al. In 2019, that did the same experiment, but here on a ResNet on Cypher 10. Again, U-shaped. There's a peak and then descent. And that's what we call the double descent. So that's a term that was coined by Belkin in this paper in 2018, because you have one descent and then a second descent. There is a second thing about this plot that I want to highlight, is that this point where the peak happens is not any arbitrary point, and actually is related to something called interpolation. And the peak is precisely the point where the training error goes to 0. So what means the training error goes to 0? Meaning that you have perfectly fit your data on your training data, which means that you have memorized. Okay? We also say interpolate or memorize. I'm going to use this interchangeably as well. So the point in which you pay the highest risk is when you start to memorize, but then even if you keep increasing the network after memorizing, you do better and better. And that's very weird. And so here is an example of, I'm just like now putting in a pictorial way, so it's not really an experiment, but this is essentially how does the situation look like back in 2018. There was all this statistical theory that says that, you know, if you overfit the data, you don't generalize. But then people have observed in some neural networks that this is not the case. You can overfit and generalize at the same time. And then people was lost back at the time. And they say, okay, there is this first regime, which is the classical underparameterized regime, which is the U-shaped part. And then the modern overparameterized regime, where you can, what we say, benignly overfit. So you overfit, but it's not bad. It's like it's good overfitting. So the question is how to make sense of that. So can we cook up a model that shows this behavior that is simpler than this? Because I don't know how to even start analyzing this, because I don't know how to write down this data distribution. 5 layers is like just too complex. So I would have to study gradient descent. You know, I would have to use some dynamical mean field theory to study gradient descent here on 5 layers. I don't even know how to write down this problem properly. So can we find something simpler, you know, on the Ising model kind of philosophy to describe this phenomenon? So the answer is yes, and now I'd like to discuss that. Okay, so what is going to be our model? So our model from now on is going to be the hypothesis class of 2-layer neural networks. So these guys. And I'm here normalizing it by the square root of the width. Just for convenience, you can always redefine A to put that back this factor there. For now, I'm not doing anything. I'm not doing anything. It's without loss of generality. So pictorially, it looks like this. So as Jaron was saying, we say it's a two-layer neural network because we count this as like, you know, 2 layers, or maybe WNA, maybe as well. I don't know. And what the problem I'm going to be looking at, given some data, I want to fit it. How do I do it? Empirical risk minimization, we have just seen. This is how people deal with fitting the parameters of the network. What are the parameters of the network? A and W. So these are my theta's that make me walk in this subspace among all functions. And I'm doing empirical risk minimization on the square loss plus potentially a regularization. So what this means is that sometimes we might want to add something here that enforces some type of behavior on the weights that we like. So for example, you know, computers are picky. If you put big numbers in the computer, it returns you overflow. So even though, you know, you might rescale all these things by 1 billion and it might not change anything in the problem, when you implement in the computer, it makes a difference. You don't want to deal with large magnitudes. So you should normalize things properly. So everything is kind of numbers which are reasonable in the computer. And so one way people do it to kind of enforce this is like to adding some constraint on the norm of the weights. And this is what is called the regularization. Sometimes also called weight decay. And yeah.
Is that just a convex function that goes fast enough at infinity, or what is it?
It could be, but not necessarily. Usually we take it to be convex, but not necessarily. It could be anything you like to enforce some behavior on the weights. So let's say that you want your weights to be sparse. Then you could put a L0 regularization that forces sparsity, but then your problem is highly non-convex and is hard to optimize. So usually you choose something convex because you want it to be also optimizable. So the typical case is the square norm, which is exactly what you said, like to keep things confined. So what is our goal? Our goal is to compute the generalization error or the population risk. And we might also want to characterize what is the training error or the empirical risk. So that's the problem. Every machine learning problem out there is composed of 3 things. So the hypothesis, the algorithm, in some sense that you want to study, which is how you do this minimization, and the data distribution. So far, I haven't said anything about the data distribution, but this is going to come later. But you should always think that these 3 factors define the problem. You change one of them, you change the problem. Might be another problem, interesting as well. But when you want to study a problem, you need a hypothesis, an algorithm, and a data distribution. So before going to how I look at this problem, let's try to motivate a bit, like, you know, how the classical statistics literature looked at this problem. So here I'm going to give you one result. I'm not going to discuss in detail, but I'm going to give you one result just for the sake of, if you haven't seen these, like to building a culture of how traditionally people think about these problems. And it's going to be what is called a uniform generalization bound. So for simplicity, let's fix the case where you have binary labels. So you're doing classification. So like you can think about cats and dogs. And if you open a statistical learning theory book from, you know, classical book from the 90s, that's the kind of result you're going to have. And let me try to motivate what this means. So the kind of result you'd like is to say is the following. The difference between the generalization error and the training error, so this is how well your training is close to generalizing, is bounded. So here is a bound. And what is here is like something that depends on the quantity of the data. So the larger the n, the closer they are. And this is because the law of large numbers should imply this behavior. Plus something, which is called here the Hadamard complexity. So the Hadamard complexity depends on the hypothesis class. So you choose a hypothesis, there is a complexity notion that defines how complex is your hypothesis. And the bound asks that this should be true for all members of the hypothesis. So for any function here, the bound should hold. Okay, so here already you see that there is something there that is not very satisfying, because as I told you like a few minutes ago, what you are interested is not at any function here, but the one that you achieve by running an algorithm. And instead, this type of result is saying, forget about the algorithm. Algorithm is hard. Non-convex optimization is hard. We don't like to deal with this thing. Let's say I want a bound that holds for any member of the hypothesis. And of course, it's going to be not very tight, the bound. The bound is not going to be an equality. But this is the price you pay for throwing away a key element of the problem. But this is what people were doing in the 90s. So what is the Hadamard complexity? Let's define it. Is this expression. It's kind of a complicated beast, but essentially let me try to motivate what is the intuition. So the Hadamard complexity is the capacity of your hypothesis class. So here there's a supremum over all elements of the class to fit labels which are random. So instead of using the true labels, you randomize the labels. Why? So here I forgot to put something important. Like this is like the expectation over y, which is, from uniformly from -1, 1. So you take with equal probability the labels plus or minus 1. So you randomize the labels. And you see how good is my hypothesis to fit on average randomized labels. So remember that our goal is to find a function from x to y that generalizes. So the key factor there is that for you to be able to solve this problem, x needs to be correlated with y through the joint distribution, which is the data distribution. So here we are throwing away the correlation. We are saying, imagine that x is not correlated to y. So that's the worst possible case, where your data, y has no information about the x. But how good is your hypothesis at fitting random data? So this should bound the capacity of fitting good data, right? Because you're taking the worst case. You're taking like how good it is. If it is good at fitting random data, means that it's also very good at fitting maybe like structured data. So with this notion, you can derive this bound. So you throw away two things. You throw away the geometry of the data and you throw away the algorithm. And the only thing that enters the bound is the complexity, the Hadamard complexity. So what the bound tells you is that if the complexity of the class is small, then minimizing the training error is close to generalizing. That's what the result is telling you, and it's uniformly over all elements. Now, is the Hadamard complexity small? Right? So, oh, by the way, I forgot to mention something just for the experts in the room. This quantity, it's very close to what is called the Gardner capacity in statistical physics, okay? So actually there's a connection between the Hadamard complexity and the Gardner capacity. And you could compute if you have like, for example, a perceptron, like just one hidden unit, computing the capacity gives essentially you the Hadamard complexity. Okay. If you don't understand what I said, just forget it. Is the Hadamard complexity small or large? So here I'm showing you a extract of a paper, which is the technical paper that introduced GPT-3. So I know it's very outdated. I made these slides this slide maybe 2 years ago. Now we are at GPT-5, but things have just increased by then. So the number of parameters in the networks have just become larger. So one way is that you can bound the Hadamard complexity by the number of parameters. And you can see the number of parameters is very large. So the Hadamard complexity is very large, which means that this result is very powerful, but is also quite vacuous for neural networks. It's a theorem, okay? So it's true. What I'm telling you is true, but it's not very descriptive, because if this guy is large, the difference can be as large as this guy. So this is a classical type of result that is the way that the statisticians were thinking about this problem in the 90s. And the reason why I'm showing you this is because I would like to stress that neglecting these two factors and going to the worst case gives you results which are very general, but not very descriptive of what we observe, because we'd like to understand this double descent behavior. And actually, there is this very nice paper that I recommend you to read called Understanding Deep Learning Requires Rethinking Generalization, that essentially empirically measuring the Hadamard complexity of real networks and showing that they are very large. So here, approximate to 1, because if you normalize this such that the maximal error is 1, so we can show that this is approximately 1 in a neural network. Okay, so here you're going to take a different approach. So the reason I'm showing you this because I'm showing you this is the classical approach. Now we are going to put our statistical physics hats and say, okay, we don't want general results. We want to make precise modeling assumptions on the hypothesis, on the data distribution, and on the algorithm. And we want to say something which has an equality instead of an inequality. And so we are moving from worst case to typical case, just like in the complexity discussion that I had for theoretical computer science. This is what worst case looks like in machine learning. Yep.
Now, person like these kind of theorems when you look into the literature, I mean, along books.
Yeah.
Sometimes they are the ones that people sometimes claims this is what is really learning in a way. So what they define like when they say machine learning, this is the kind of things that shows that the algorithms are learning. Is it that so? This is an old-fashioned way of looking at it.
So I kind of feel your question that. So when I started doing research in this business, when I was going to the machine learning conference or the big machine learning conferences, where all the community comes together, both practitioners and theoreticians, if you go to a theory session, you'd see that most people will be discussing generalizations of that. So you could go into directions that generalize this to make this better. So one example is what is called pack base, for example. So because this is what's called pack learnability and VC bounds, uniform bounds. So you could go into the direction of trying to save this type of results. And this was what most people was doing in theory, maybe 10 years ago. What we are going to be doing is an alternative to that. And it's true that it's not the canonical alternative. Like, so most people in this community, they are thinking classically in this way because they come from this tradition. So we are kind of the weird people in the room in some sense, trying to make strong assumptions and trying to go, let's say, from bottom up instead of top down, right? Both approaches are valid. I think both approaches should coexist. But it's true that there was a certain prejudice of people that have been doing statistical learning theory towards people that were doing what I would call exact asymptotics, which is not necessarily statistical physics. So statistical physics is one way of getting these results, but you can also get it mathematically, rigorously. There are people doing this who are not physicists, but we were the minority. And my feeling is that from 10 years ago to now, is that the community that is trying to get exact results under strong assumptions is getting more and more place and is more and more accepted in the theory community of machine learning. And people doing this is still there, and I think they should be there. Like, I mean, I think that the problem is hard, and we should all be trying to approach it from a different point of view. But I would say that nowadays there is less and less, there's more and more acceptance of what I'm going to be telling next. And the reason why I told you the history of machine learning and statistical physics was exactly because of that. There was a period where, as I showed you, like Yann LeCun and Michelangelo Virasoro were sitting together discussing neural networks. And at the time it was very natural to have this type of, like our type of perspective on the problem. For some reason that I don't want to get into, because I also don't know so well the historical evolution in the 2000s, there was a disconnection. And the people who kept doing machine learning theory at this time were doing this. And when physicists came back to machine learning theory, because I told you, physicists never left the helm of this interaction, but they were focusing on other things like theoretical computer science, typical case complexity. But when people went back to machine learning theory, there was a bit of a misunderstanding between the two communities. And the people that the young generation doing that don't know the history of that we were there in some sense back in the 80s. So that's why I tell you the history, because I think it's important to remind as well that it's not as if our alternative approach is like crashing into someone's party. It's like, you know, we were part of the party since the beginning. It's just that we left for a little bit and we came back now. Yeah, I don't know if this answers exactly your question, but it's my perspective on that. Okay, so let's get going. So data model. So I told you that instead of doing this, we are going to be making assumptions. And here it starts like the strong assumptions. And, you know, I hope that you share this perspective with me, that strong assumptions are good. And the whole point about doing strong assumptions is to improve them little by little, like, right, getting closer and closer to the truth. If the truth requires the stronger assumptions, because sometimes simple assumptions are already enough, right? Sometimes two-body interactions is already enough to describe phase transitions. You don't need to go to crazy, like, you know, you need to use the Hubbard model to describe everything. So what is the assumption I'm going to be making here on the data? So I'm going to be assuming, so here I'm specifying the data distribution. So I'm going to be assuming that my labels are generated from my inputs, X, through a nonlinear function, which is a projection of the data across R directions. So there is a linear part and a nonlinear part. And so why this is a good assumption? So let me maybe say a word about that, is that you can prove that in the worst case, the number of data that you need to learn a certain function is exponential in the dimension. So if the dimension is large, in the worst case, you pay exponential price. So this tells you that you require assumptions. So one rationale is to say, okay, data is not in dimension D. It looks like dimension D, but the structure in the data is such that the real information is in a subspace. That's what is called the manifold hypothesis in machine learning. So this is modeling the manifold hypothesis. It's telling you that the subspace, the informative subspace, is not in dimension D, but in dimension R. However, the relationship is not linear, because otherwise you just do PCA and you would be able to recover the subspace. So we add a nonlinearity which correlates the different directions such that it's non-trivial to invert this function. So these type of functions, they are called multi-index models. And we say that the relevant information, which are the W's, are what is called the indices. Okay? So for simplicity, we're going to assume that the indices are all orthogonal. So we sample them from the sphere and we fix them. So, you know, this is really a R-dimensional function. If these guys were starting to be correlated, I would have to remove the correlation and maybe this would lower the dimension, R. R is the effective dimension of the data. D is the dimension that I observe. And then I'm going to be assuming that X, the input data, is completely unstructured, is Gaussian IID. Now, this is super strong. If you look at the cats and dogs photos, like, it's not IID. The pixels are not IID, and there is a whole bunch of structure there. So here I'm throwing away this structure, and I'm making my mea culpa for that. What happens when you add structure here is a very interesting question. I have been working on that over the past 4 years. But you start somewhere. So I'm not telling you that the problem is unstructured, okay? I'm just telling you that all the structure in the problem comes from the dependence of y in x. So there is no structure on x itself. So all the structure is in this part of the problem, not in this part. So the problem is highly structured, but the structure is only on one side of the problem, on the labels, not in the data. So let me give you some examples of functions that take this shape. So for example, if you have one index, r equals to 1, the linear function is a multi-index model. So that's nice, linear function, we like linear functions. So the phase retrieval problem, the one that I showed you on the case of inverse problems, where you take a one index and you square it, is a multi-index problem. And then the physicist's favorite, the binary perceptron, right? Like the labels are binary, and then you take the sign of the projection, is also in this class of functions. So we are happy. Some of the problems that we like are in this class of functions. But other crazy things are also in this class of functions. So for example, if you take more indices, you can take any polynomial multiplying this direction. So like say monomials like this, but also summing different degrees. They are also multi-index functions. The sign of the products is also a multi-index function. So this function here is the favorite function of computer scientists. It's called the parity function. Actually, to be precise, is the sparse parity function. And so if you're a computer scientist, you know this. These are one of the hardest type of functions to learn in learning theory. So it's nice because we can go as hard as computer scientists like in this class of functions. And then our friend, the two-layer neural network, is also kind of a multi-index function. So you can build a two-layer neural network by taking this function to be a separable sum of some A and sigma. So it starts to make sense because we are fixing the hypothesis to be a two-layer, and then we choose our data distribution to resemble a little bit the two-layer case. So we could have taken something harder, right? But if you're choosing the hypothesis to be two-layer and you're learning something harder, means that there is something probably you cannot learn. So here there is a game that physicists like to play when they do this business, which is called teacher-student models. So teacher-student models is that you choose the data distribution in a similar class to the hypothesis that you want to study. Because you know that if you choose the hypothesis to be simpler than the data distribution, then you cannot learn the part which is orthogonal to the hypothesis. And vice versa. If you choose too simple and you choose a hypothesis which is too large, the problem is easy. So the kind of right amount of complexity that you want in your problem is such that the hypothesis is of the same complexity of the data distribution. So this is essentially what we are trying to mimic here as well. So you can see this is a teacher-student model if you have come across this language. So I guess I have a few minutes. Let me get into the next slide, and then we can take from here like tomorrow. So we said that we are going to study two-layer neural networks. And we are going to say that we said that we're going to study them in the simplest setting first, which is where the weights are frozen at initialization. So this is the problem that I want to solve. The minimum over the square loss over the two-layer neural network. So here I'm putting a square regularization, and you're going to see why I'm putting a square regularization. And so the first simplification I'm going to make in this problem is that I'm going to say, okay, if I minimize over both A and W, this problem is hard because it's non-convex in W. It's a problem that is convex in A, it's a linear problem in A, but it's a non-convex problem in W because this is a non-linear function. Okay? So the first step is going to say, let's simplify life, let's freeze the weights W, and let's just optimize over A. So we are back to the convex world, where things are a bit simpler. Well, in this case, I can derive an explicit solution to this problem. So I can just, this is a square problem, this is a quadratic problem. I pick my regularization to be quadratic. So this means that I can find an explicit solution. It's a convex quadratic problem. So if I do the maths, I take the derivative of this loss function and I find the minimizer. The minimizer is unique and is given by this, which is essentially the resolvent of this matrix. And what is this matrix? This is what we call a feature matrix. So that's the sigma of x W0. W0 is the frozen weights of the network, and x is the data. And that's a matrix in n times p. So p is the number of neurons, n is the number of data points. And we should kind of be happy about this because this is a random matrix theory problem. I have x is a Gaussian matrix. W is uniformly from the sphere, right? It's frozen. I have a nonlinear function of them. I produce a matrix. This is a random matrix. And I need to compute something related to the resolvent of this matrix. Now, it's not a simple random matrix theory problem. So if you are used to random matrix theory, you're used to Wigner distribution, you're used to Wishart distribution. This looks like a Wishart. but it's not really the usual Wishart, because it's not like, you know, Gaussian matrices that are, it's not like Gaussian transpose a Gaussian. It's like a nonlinear of the product of a Gaussian with something that looks like a Gaussian as well, which is a uniformly from the sphere. So this is not a simple random matrix theory problem, but it's a random matrix theory problem. So we know how to approach this. It's just that we need to do something more complicated than the usual random matrix theory textbook kind of calculation. So that's the challenge. There are many results for the case where phi is Gaussian, but here phi is not Gaussian. However, something is going to come to our rescue, and this is going to be, again, the blessing of high dimensionality, as I introduced last time, is concentration in high dimensions. So let's take this matrix and see what is the hard part of this matrix. Is the nonlinear part, right? So what is inside the matrix is kind of standard. It's a product of two Gaussian-like matrices. The nonlinear part is the hard part. So what should you do when you have a nonlinear function of a Gaussian? You should linearize the nonlinearity. So you should expand in a basis of polynomials, for example, that is orthogonal with respect to the measure of the inputs. So here is Gaussian, so I'm going to take the Hermite polynomial basis. So I can always write sigma of the entry ik as the sum over all Hermite polynomials with some coefficients of the argument. So just a reminder for you about Hermite polynomials. So Hermite polynomial alpha is a polynomial of degree alpha, and they are orthogonal with respect to the Gaussian measure, meaning that if I take expectation with respect to the argument of two Hermite is equals to 0 if alpha is not equal to alpha prime. And since this product here is the product of two Gaussian vectors, is the scalar product of two Gaussian vectors, the argument of the polynomial is a number which is of order d to the minus 1/2. Because if you take two random Gaussian vectors and you multiply, you take the scalar product, the typical magnitude of that is going to be d to the power minus 1/2. So meaning that when d is large, the correlation goes to 0, right? So Gaussian vectors are orthogonal in high dimensions. And in finite dimensions, they are not orthogonal, and the scalar product scales as d to the minus 1/2. So now this is a polynomial of something which is d to the minus 1/2. So this means that the whole thing is a number of order d to the minus alpha over 2, meaning that higher frequencies in this sum are decaying with d faster and faster. So I'm doing a frequency decomposition, high frequencies decay faster. Great. Let's compute the moments. So the average is the first Hermite polynomial. Let's compute the two moments. So this is the expectation of this object. As a good physicist, I take the indices to be different because they are dummy indices. I take the expectation inside the sum. I have a double sum, alpha, beta. The coefficients are outside. Expectation with respect to x. And so this is expectation with respect to x of alpha, of the input, and beta. I now use orthogonality. So this means that this is non-zero only when alpha is equals to beta. And then since the arguments are different, you get the scalar product between the weights to the power alpha. Delta alpha beta. And so just this is the same thing I did. If you expand the expectation of the second moment, I have first Hermite square, second is like, so the zeroth order Hermite square, first Hermite square times the scalar product plus the higher frequency part. And the higher frequency part is essentially given by this. And since these are uncorrelated, they also scale as d to the minus alpha over 2. So actually, the only terms which are order 1 in this sum is the diagonal when k is equals to L, because then you get the norm. The norm is d because they were in the sphere. So you get 1. So you get the sum over alpha square. But if you take the off diagonal decays as minus alpha over 2 if d is different from, sorry, if k is different from L. And so essentially, when d goes to infinity, to first order, I just need to keep the diagonal term, which means that effectively, this covariance matrix that I need to deal with to first order is just a diagonal matrix plus the scalar product of the weights at first order plus a spike, a rank 1 term. And then you can check the decay moments, decay as Q moments as Q over 2. And that result is what we call Gaussian universality. So that's what we call the Gaussian equivalence theorem, is saying that this random matrix theory problem in high dimensions, essentially, even though the features are nonlinear, is effectively as if it was linear. Okay? Because this, so if you see this is a Gaussian matrix, so this is just a traditional Wishart matrix, which we're shifting by a diagonal plus a spike.
How do you get that any IID distributed random matrix if you win, right? You make the same kind of argument.
So it's not the same, right? Because here, if you just say that this was if phi transpose phi was within the Wishart universality, that would be a Wishart with not like this spike and this diagonal, right? So this is not just standard random matrix theory universality. This universality is only true asymptotically as well.
But that's also true in the same.
Yeah, that's true. Okay, yeah, good point. Yeah, but you would not have the right matrix, I think, if you just do standard.
Constantly central.
But
yeah, it seems very similar.
Okay, we can discuss offline and see if it falls within the standard universality, but I don't think so. I'm not sure you get this spike, this rank 1 part. Okay, just to finish because I'm running out of time. So the point is that we can map this nonlinear problem, which was the hard part of the random matrix theory, to an equivalent model where instead of taking the nonlinear features, we are changing it for a Gaussian matrix, which has the same first and second moments, where we have to carefully like add this diagonal part, which becomes a Gaussian matrix with the right second moment, and this spike. And the theorem tells you that the risk, so the generalization error of the original model on the nonlinear features equals to the risk of the Gaussian problem in the limit. In the limit where n and p go to infinity at a proportional rate, which is called the proportional limit. However, notice that this argument can be generalized. If you'd like any polynomial scaling, let's say n is equals to p to the power 2, you just need to go one order further in this expansion, and you would be able to deal with that. So that's what's called Gaussian universality, and that's what allows us to study the risk of this very simple 2-layer neural network with frozen first layer. And let me finish just making a more general comment about that. So this is a result that appeared concurrently in a paper by Song Mei and Andrea Montanari, and a paper with Sebastian Gold, Marc Mézard, Lenka Zdeborova, and Florent Jacala, more or less same period in 2019. So Sebastian was studying this in the context of dynamics. So together with him and also Marc and Lenka and Florent, we generalized this to the random matrix theory case where we learn from a finite batch of data, not during the dynamics. And more or less at the same time, there was a proof by Yue Lu and his student that proved what we did heuristically using essentially the argument that I showed to you. And this idea of Gaussian equivalence has been generalized all possible directions. So if you want to do a deep network with frozen weights, you can derive some Gaussian universality to deal with that. If you want to go to polynomial scaling, you just need to go higher order in this expansion. If you want your data to be multimodal, so instead of one Gaussian, like a Gaussian mixture, you can do it as well. Conditionally, you have a universality conditionally on the weights, on the modes. We have checked that you can apply this type of results like to real data and to some extent work. So I'm going to discuss next time when it doesn't work. And you can also use the standard universality on the top of this universality to relax the fact that X is Gaussian. So as long as X has, I don't know, I think finite fourth moment, you can derive universality of the features. So the feature is the matrix phi for more general X, as long as X is let's say, well behaved enough. So, okay, I'm out of time. Next time, we're going to keep doing this. We're going to see that we can derive formulas using replicas for the test error using universality and discuss the phenomenology of this model. As you can see, it has this double descent behavior that neural networks have, and we're going to discuss why they manage to reproduce what you observed in practice. So this is for next time. Thank you for the attention. Question? Oh, hey.
The thing that severely breaks random matrix universality usually is when you have correlations between the elements of the matrix. So if the weights become correlated, say in the training process, do you lose Gaussian universality, or is it a way to
Okay.
recover it?
So that's a very good question, because as you train, the weights do get correlated with the data. You break Gaussian universality, and in order to be able to characterize the performance of the train network, you need something which is what we call conditional Gaussian universality. Essentially what we show, and we're going to get there, but essentially what we show is that after one step of gradient descent, the correlation is essentially a spike on the top of a bulk. So conditioning on the spike, you can apply standard Gaussian universality on the rest, on the bulk, and then you treat separately this spike that correlates with the data, and then you get the benefits of learning on the top of the initialization. And then you prove that neural networks that learn are better than neural networks which don't learn the first weights, and you prove the separation result. So this is like a result from 2 years ago, but it exactly goes in this direction.
So we have a topic, right?
That's all. Well, let's talk about it.
So I guess your question is whether, so if you center the matrix
Yeah.
and you match the second moment,
Yeah, exactly.
whether you can apply just a standard like Wishart universality.
Yeah, I mean the standard arguments where you make this the field theoretic representation of the resolvents, and then
Yes,
you make
yeah.
the expansion in large N, and you say, oh, only these diagrams matter, and it's Gaussian. Yeah.
Well, no, that I definitely think you can do.
Okay.
That I definitely think you can do. What I had in mind though is that whether you could dissatisfy the standard assumptions like on the proofs of Gaussian, like of Wishart universality.
I mean, I don't know this. I know the physicist said, right? Which is
No, but I think this is true. I think this is true.
Besides, you say, the reason there's universality, that no matter what the IAD distribution is, as long as it's finite second moment and as long as it's centered,
Yeah.
then you'll get the same resolvent because the diagrammatic expansion for the resolvent has factors of n.
This I think is true. Now, the reason why I'm a bit not 100% sure
Sure.
is that the result that we have to prove, it's not that you have universality on the level of the matrices,
Yeah.
but you have universality on the level of the error. So you see, the statement I made is not that
Yes.
it's not that the distribution of eigenvalues is the same.
The error is what it's the resolvent, but then you have the resolvent and the product into something.
Like it's traces of products of
It
resolvents.
was like the resolvent with the product of the matrix itself, right?
Yeah.
Then another vector.
No, but then you need to square this thing, and you need to take the expectation and get a trace. I can show you the expression, but it's essentially you have three terms which are traces of products of
I
resolvent.
mean, I agree. This is not a typical thing you can do to run a matrix theory.
And the key point is that if you look at spectral properties, so for example, universality on the Frobenius norm is not true. And in operator norm, it's true, it's universal. And on the risk is also universal. So when you compute the error, meaning that the part of like which is non-universal doesn't matter for the error in the scaling. So that's what is makes me not 100% sure about.
No, it's fine. I mean, and when you start making these crazy nonlinear products of matrices, things change.
But the right place to see this is like there's a paper by Sandrine Pechet and Lucas Benini, who are two mathematicians working on random matrix theory, and they have a discussion of that in a paper in 2021, a rigorous discussion of that, and they show exactly what things on this matrix are universal and what things are not. Yeah, but we care about the risk, so we just because we care doing the replica computation.
Yeah.
And indeed, in the replica computation, you just change for the Gaussian matrix, you compute the risk, then you fit the moments you put there, and you get the right result. And the proof of this result by UA is also on the risk. It's not on the matrix.
No, that is different. That is different.
Yeah. Let's have coffee.
But it's a rhyme. It's a kind of rhyme. Like it's an extension. It says it's stronger
Yeah.
than universality.
Yeah. Stronger. I mean, I think it's weaker universality in some sense. No,
No, but in the sense that I would expect to see, okay, that the spectral densities should be the same in the Gaussian case and the Gaussian case for that phi matrix, right? From their end matrix picture, right? And you're saying, oh, it's not just spectral density, it's also some crazy series of nonlinear function of the matrix, which you wouldn't necessarily be able to guarantee by just having the spectral densities match that the two things would be the same.
yeah.
Right?
Yeah, exactly. And also on the top of like there are some spikes which are there that don't matter for the risk.
Yeah.
There are spikes that matter for the risk, spikes that don't matter for the
This is
risk.
standard thing also with complexity, right? Is when you have these few eigenvalue, low rank perturbations, you don't see them at all at the field level.
Yeah,
These,
yeah. Because the resolvent is an aggregate. But in the case you ask in the end, like this spike when you learn the features, when you do gradient descent, these are spikes that appear because they are order D spikes.
Yes.
So they modify the bulk on the order one,
I see.
and that's why they are.
But do you also have problems if the data is correlated? If the beginning data, because I think your matrix was the products of the weights.
Yeah,
of the
so
data,
that's
so
what
the
we-
data is correlated.
So that's what we have been working for the past year and a half or so. We have results, but they are not as satisfying as these results. Let's
Okay.
say it's not as sharp.
Gracias.
Gracias. Gracias. There's a terrace. Go see the view.
I mean, so yeah, last semester I taught a class on matrix theory, purely
Oh,
from
nice.
this perspective, right? So now you think less pollution than it deserves for the size, dirtiness, because it has that plateau, so blow things away. It was crazy, like there are like in Sao Paulo, because Sao Paulo are hills, right? So you have like local topography, which does make very strong traps. Like for instance, near my house. Yeah.
Gracias. Gracias.
Near my house is this deep ravine that used to be a river, right? Now it's some road.
Yeah.
And it has like a big road on a bridge over it, right?
Mhm.
I often bike over on this top road over the kind of cut where the road is below. And this thing is like a perfect smog trap. And on days when it's not windy or hasn't rained for a
You
bit,
can see the.
see the smog settled below, like it's mist in a valley. It's crazy. But it's hyper local.
Yeah. Can we bring
Viaduct as well.
viaduct? Yeah. It's they have some books. I'm gonna take a look at the. Some kind of academic. No, not physics.
Oh, sorry, I
That's
had
okay.
lecture.
Ah, you were teaching this morning.
Yes.
What you were teaching?
Huh?
What you were teaching?
A lab for electricity and magnitude. So,
Ah, okay. Good.
yes. So last week we were in a strike, and this week we had lectures again. So, yeah, and I didn't realize that I could follow your transmission by YouTube.
Oh.
So now I have the transmission. So
Okay.
I will.
Ah, so it's recorded.
It's recorded.
Okay.
So
Okay.
we will-
I need to be careful because I think
everything's online.
yeah, I need to be careful because I'm bashing a lot of computer science, I think. So I hope that none of my colleagues is gonna actually watch this. Yesterday and today, I think I said some bold things about computer scientists.
No, but I would like to suggest your course and your lecture and your recording to the people of
Oh no.
computer sciences.
So I have some lecture. So I gave a similar version of this lecture for computer scientists in a probability conference last year. It's called Informs and was recorded.
Okay.
So I think that's a more adapted because yeah, it uses more the language and
Okay, perfect.
so I can send to you the link. So it's all in YouTube. Yeah,
Okay, please.
it was in Atlanta last year.
Yes, because yesterday when you started, I wondered, I didn't give the information to the people of computer science.
Oh, okay, yeah.
Like, we have computer science in two places, no? In the science faculty, but also in the engineering.
Engineering, yeah, of course, yeah.
Yes.
Also electrical engineering, I guess that some of them because all of this is kind of touches different areas. So there is a very theoretical computer science part. There is a signal processing part, which you touch with the engineer, like the electrical engineers.
Yes.
There is more applied mathematics side. So you can find people interested in this kind of topics like a bit in many departments, especially in the US. I mean, in France, the departments are organized in a weird way. So yeah, we don't have the same organization as in here and
So, yeah.
Brazil and the US as well, which is similar, I guess, to here. So yeah. We don't have actually electrical engineering is very small
Okay.
in France. So
And how it was today arriving here and yesterday? What did you do?
so today is very easy here, yeah.
I just walk.
Yes, you are in this hotel, no?
Yeah.
So I walk from Candelaria as well, so
Yeah.
very easy. So yesterday we walked in Candelaria a little bit,
Okay.
bought some coffee, some chocolate.
Okay, great.
So the coffee can be very expensive.
Yeah, the coffee is very expensive.
I don't think, yeah.
Hola, ¿qué estás? Bien, bien. Qué gusto saludarte.
Alma Valencia.
Nice to meet you.
Alejandro. How are you? How is it going?
Huh?
How is it going?
Good, yeah.
Yes. Yeah,
I'm glad to hear that.
yeah.
So now I sit there to attend the talks. Okay.
Yeah.
See you.
See you. Yeah, so the coffee can be very expensive. We went to one of the coffee places. They suggested me a very premium coffee,
Yeah.
which was 120,000.
What?
Yes.
No, o sea,
It was fancy coffee.
yeah, coffee is expensive, but not as much.
No, like
No, but this was a-
coffee.
But,
Beans.
okay,
But the premium, like a specialty coffee,
okay.
like a small producer from a specific region, specific variety. But even that, so in France, I buy Colombian coffee.
Yeah.
Oh, so this is still here. So in France, I buy Colombian coffee. Yeah. So I buy Colombian coffee, and very good,
Yeah.
premium kind of coffee. But I think it cost, I don't know, 11 euros, 12 euros, which would be maybe 70,000 or a little bit less.
I don't know. I don't.
Yeah. That is more or less what I pay for 300 grams of a place that you say, no? I know the place, the
Yes.
producer and so on. Yeah.
So this is what I pay in France. But then I went to the fancy place here. We went together, and there were 70,000 for like coffees, but the best one they suggested me, I said,
Yes.
what is the premium coffee they? Wow, 30 euros.
The best one in France also will pay a lot.
I don't think you find that one, like, or not in the place that I go.
You have to take the one that has the animals eaten and then pooped out again.
Ah, yeah.
Yeah,
Indonesia, no? They have that.
In Africa, there's
I-
cats. There's cats. that are-
And in Brazil, you know, as well.
Oh yeah.
So we have
Yeah.
a version of that. It's a bird in Brazil.
Ah, okay.
It's called jacu, I think. So my mom knows the guy who owns the farm.
Very nice. So you
So
see
what?
you the source.
They're not friends enough, I think, to get like supplies like for free.
Yeah.
But he built this by just copying Indonesia. No, this bird also exists here, so I should try to do it.
My they also use elephants. The other elephant coffee, they use the elephants poop it.
Yeah.
Was the civet cats. I guess there's birds. Also in Indonesia they use birds.
So
I do have the
it's
elephant.
it's like it's a bird called jacu. It's a black bird. So I don't know. I don't know if he copied it from somewhere. It was not something native to Brazil.
I mean, basically any animal that voluntarily eats the coffee cherries but doesn't digest the bean
Yeah.
is the same thing, right? It's the idea that you have semi-digested the bean.
Yeah, but I think that's not obvious, right? Like, yeah, I think humans, for example, like they do that. You eat the coffee, like
Yeah, I guess you have a farm people doing this. You have to clean the beans well. Like,
no, but I don't. I think we do digest the beans.
oh yeah, okay.
Yeah, I mean, so when you eat these chocolate beans, like you know,
Oh, we chew on them.
but they don't.
And they've been cooked. Take a raw coffee cherry
That I don't know.
and swallow it.
That I don't know.
And see what happens. They come out. I mean, I don't.
Please don't.
But the ones that you have in chocolate roasted each other crunchy, right? They're super roasted.
Yeah, this is. So I don't know how to. I actually never tried to taste like how the beans.
Very bitter.
Bitter. Oh,
It's like eating carrot.
I think people on Zoom was listening to all my conversation. Outside. No, no sé anything bad. ¿Para qué?
Para listo. Entonces, espérame, abro esto desde descargas. Clipon, uploads. Aceptar, I guess. Y sí, entonces tienes que creo que hacer eso. Sí, control L. Ah, vas a esconder los cositos. Sí. High floating meeting controls. Y aquí es. Cuando quieras.
Okay, welcome back. We haven't already talked about
Oh,
all yours. I'm sorry, I didn't realize.
thanks. Let me close this door. Okay, thank you, everyone. Thank you, Gabriel, for inviting me. I'm gonna try to make this in 15 minutes, which is, I think, is what I have. I choose to talk about a little piece of the research we have been doing research recently. So I'm going to show basically a statistical kind of approach to understand how we can make better memories for applications to machine learning and chips that can do actually faster machine learning computations. So what we have is the following. So in the ideal world, so in the device that you are working on to make a neural network, so you have a combination of bit lines and word lines. So every dot here is a single neuron, and that neuron has some material properties, which I'm not sure if you are familiar with. Typically, they are some sort of a combination of transistors or resistive materials. And what they do is that they change the conductivity depending of the signal that you send. So the bit lines are the ones that you send a pulse and the material changes its properties, typically their conductance or resistance, and the resistance changes in a way that it can have a memory. So it has either one value of resistance or another higher value of resistance, and these two values can be used as control of the synaptic weight, for instance. So even that kind of particular description is still a subject of a lot of research right now, because the materials that you put here well, it has to be kind of compatible with silicon, at least right now, and then it has to be scalable. So that's kind of the idea. So what I'm going to show today is research in material science, where I'm going to propose a specific group of materials that can be put into here that can have not only two particular values of resistance to change the conductivity, but it can have multiple states. And if you have multiple states, you have a chip that is completely configurable, that it can be programmable to any task that you want, because it has many level states of synaptic ways to play with, okay? So, and that is called neuromorphic approach. So the idea is to make these devices similar to exactly how the neuron works. In the particular talk that I'm going to show you today, so I'm going to focus on neurons. Neurons means that you have you have a threshold voltage, and if you send a signal above that threshold, then the neuron will spike, and that spike will send some information to a neighbor neuron to do something. Okay, and so the synaptic weight that I'm going to show here, it will control at which voltage that particular neuron will fire. So in that sense, this is kind of the device I'm envisioning here. Okay, So the material. So this is kind of a complicated material for some of you, I guess, if you don't have a background in material science, but I'm going to try to make this as simple as possible. So it's something that is called manganite. It's a particular group of materials that has a manganese as a center kind of the physics of the problem. And it has a cube structure. And in the particular manganese I'm going to show today, is a combination of two groups of manganite systems. So it's this stoichiometry here. So here is the manganese. And then we have a combination of lanthanum and calcium in some particular sites here in this crystal structure. And the praseodymium calcium manganese oxide that has different physics properties. So what we have from this material in particular is that we have something called magnetoresistance, colossal magnetoresistance to be precise. And then that means that if you apply a magnetic field, you will change the resistance by a lot, like colossal kind of, so orders of magnitude. The praseodymium instead is kind of an insulator of the time, but it has a mixture of ions, in this case, manganese 3 plus and 4 plus, and that extra electron there changes a lot of the magnetic interaction. So the type of interaction that this controls is that by itself, it has a phase coexistence of regions where it's rich in manganese 3 plus and other regions that are rich in manganese 4 plus. So depending on the ion that is there, so the orbital, the driving orbital is different, and you have kind of in an overall picture, you have a chessboard kind of like domains. So you have these particular orbitals aligning with the manganese 4 plus in this way, creating a ferromagnetic strong correlation or antiferromagnetic strong correlation if the orbital is more or less that way, kind of perpendicular to it. So what we do is that we combine these two. So these by themselves are very complicated, and we complicated it even more by mixing these two together. So we mix these two, and then the idea is that we are going to have in these sites where the lanthanum and calcium combinates or mix, we are going to have also praseodymium. So the idea is that we are going to have the best of the two worlds. So we are going to have the metal insulator transition of one of the parent components, and we are going to have the phase coexistence of the other component. And then the idea for that is that if we can tune how much we have from the other, from both of them, we can have phase separation, and the phase separation will give you a metal insulator transition, like a colossal metal insulator transition. And that's exactly what we got. So this is the phase diagram of one of the parent components. This is the other one. And then if we mix these two by a specific ratio of 5:8, so we get something that looks like this. So the phase diagram of the material I'm going to talk today, which is lanthanum, praseodymium, calcium, manganese, we call it LPCMO. So it has a complex phase diagram. So this is temperature, this is field, and then depending of where you are in this phase diagram, so you have something that is completely antiferromagnetic, you have something that is ferromagnetic, but the magnetism there is completely kind of strange. It's kind of a fluid. It means that if you put a magnetic field, the domains actually shift as a fluid. And then there is a region where those domains actually freeze. So it's kind of a solid, ferromagnetic solid phase. And then it means that it's some sort of a spin glass, kind of crystal glass, I think is the best description. So this is the material that we are going to work with. So this is what I was trying to induce before. So this is the actual device that we have. So this is the resistance as a function of temperature. And you see that when you cool that sample down, so you get, this is kind of a normal or kind of similar to a semiconductor device, or something that is insulated. But at some particular temperature, we call it the metal insulator transition. It goes down very sharp and by several orders of magnitude, and then it stabilizes at some particular value. And then you go up in temperature, you have this funny looking hysteresis, this region here, which is a plateau. And then you have this kind of hysteretic region, which is kind of interesting. So the idea or the physics here is that by having this metal insulator transition, we are inducing ferromagnetic domains into the sample, which are ferromagnetic. And then those domains percolate, and the percolation threshold happens exactly to this point. So you have a network of ferromagnetic domains that connects, and then that's why the resistance goes down so abruptly. Okay, then we have the magnetoresistance effect. So here I'm plotting the same resistance, but now as a function of magnetic field. So if we are at some temperature, let's say 100 Kelvin, so we are in 100 Kelvin, so we have some particular value of resistance, but if you shift the magnetic field, then the resistance will go down by several orders of magnitude. And then if you decrease the magnetic field, you get the same effect, but you get to a lower resistance value. So many things we can discuss about these figures. For instance, if you notice, there is kind of a jump here, and there is many jumps here around. So this is exactly a percolation phenomena. The jumps follow a power law distribution, and this is exactly also some sort of a kind of percolation threshold, but induced by magnetic field. And the reason for that is that, as I said before, these metallic domains are ferromagnetic, and when you apply a magnetic field, part of the phase that is antiferromagnetic converts to a ferromagnetic due to the strong magnetic field, and then the magnetic field drives the antiferromagnetic phase to the low temperature. Oh, really? Okay, so yes. Yeah, for this particular one, yes, there is slightly fluctuations. This one, because we are measuring a huge sample, is more or less the same every time. And I just was told that it's 5 minutes left, and it's only like 5% of my talk. So, okay, let me think, what should I do? So here, what I have is now because I want to use this as a device, I care about the IV characteristics, so the current and voltage behavior. So here, I'm showing you what is the voltage and current characteristics, and you see that also there are some jumps into the systems, and then into this particular sample, and then you have a value where the resistance drops. This is completely different to whatever material you remember from your courses, because this is completely different, and the key factor is that you have this value here, which is the resistance, if you calculate the local resistance here, so you have a huge change in the resistance, okay? And then this is reproducible, so if you do several cycles, the resistance changes a little bit, but it's more or less the same behavior. Here is a bunch of cycles of IVs, and here I'm plotting the resistance, local resistance, as a function of time, okay? And there is a region where I am at high temperature that this doesn't happen, so it doesn't have a memory effect, but the resistance do change. So basically, this is what I'm calling non-volatile and volatile memory. So this material has both behaviors. So I can induce a regime where the sample will remember at what temperature was fired, and there is a region where it doesn't remember, it just change, okay? So what I did with this material is that we did this resistance as a function of temperature again, but we choose to reverse the temperature before we cross this 180 Kelvin, which is where something called charge order, where the sample enters into a charge order phase transition. So if we go back, now the sample remembers that was at this particular temperature, so remembers where the value was reversal, and then instead of going to this value, it goes to this value here in green. That is even higher change in resistance, is almost 5 orders of magnitude, so that's a lot of change, and that can be melted also with magnetic field. So this is just to show that it's a memory effect. I can stabilize different resistance values. And then if I plot the resistance at 2K as a function of the reversal temperature, I get this value here, which is also very strange. So there is a reversal temperature at which gives me the highest value at 2 Kelvin. Okay, and the same for the magnetization. I didn't show that before, but then you can control also the magnetization of that sample. And that is what I wanted to show you today, which price up recursion model can actually fit the results. Let me skip that. Probably you know the price act model for fixing things. If I assume that sample is a bunch of histons or small regions where they itself have a metal insulator transition and has a magnetic and antiferromagnetic properties, and then I put a lot of them in a distribution with different TCs, then I get okay, I'm gonna skip this. I can actually predict that there is a well-defined equation that takes into account the phase fraction of the magnetic domains. And then I can, if I include the fact that when I go very low in temperature, when I apply a pulse, a current pulse, or when I go down in temperature, when I go back, what I'm doing is that I'm not allowing all the domains to switch back. So I end up with a system that is more insulating because there is no percolation threshold anymore compared to the fact where the sample is at equilibrium. So this is the behavior of the resistance at 2K obtained from the model. And then if I plot everything together, like here, so I get the resistance. These points here are the curve that I showed you before. So this is the 2K resistance values. And then the line is the simulation, assuming that every time you go in temperature and go back, you have a not complete reset of the magnetic domains. So this simple model can reproduce the resistance value and the magnetization curve at low temperature. So the picture here is that by calculating this price model, I can show that for some particular regions, so what you get up when you end up at low temperature is that a region where you either have a percolation threshold or it's not completely, and that's why you have this huge. And the message here is that you can use this truncated percolation model to basically use it as a memory device in neuromorphic computing. And I guess I will end up with that. Just let me, oh, I think this is my summary slide, yeah. Okay, yeah, that was. Sorry, that was very fast.
Thank you very much.
Yeah, I don't know if it was clear enough, but yeah, go ahead.
Okay, I am not from solid state physics, so
That's okay.
when you show can you see the slide when you have the orbitals, pointing to the manganese? So this is the basic structure. So how these orbitals are oriented is the basis of everything.
Pretty much, yes. So it is for the case of the praseodymium calcium, but yes, when you combine the two materials, so there's the same property kind of mixed with everything. So yes, the whole idea is that you have a balance between manganese 3+ and 4+, which give you a completely different orbital ordering. And the whole idea here is that orbital ordering will determine if the sample or a region is metallic or insulating or antiferromagnetic or ferromagnetic. That combined with other stuff like disorder, but the basic physics is in the orbitals.
So it's something like you have many metastable states like in a glass system.
Yeah, so yes, that's actually you can control how much metal stable states you have controlling the doping. So here I choose something so that the ratio of this stoichiometry that I show is close to the where that disorder is not enough. It's not too much. But depending on the disorder, you can have like a completely different physics, something like a Griffith's phases, like a bunch of
What is the price model? I don't know.
Oh, yes. I thought that it was kind of known. Yeah, the Price model is assuming that this explains your system. So when you have, so this is the model. So the model is assuming that you have a sample or something that can be discretized by different kind of domains. And each domain has the properties of the whole. So if you see, so this particular domain has either insulating or metallic behavior, and it has a ferromagnetic or antiferromagnetic behavior. And then I basically create a matrix of all these little kind of domains, which in the model are called hysterons. So I put a bunch of hysterons together, and then I calculate the whole magnetization and the whole resistance. And that gives me exactly reproduce everything.
Distribution of sizes or something.
Yeah, so I got you have to assume the distribution of sizes if you want to, yeah, if you start from scratch, yes. But what I did here, it was to assume, so I use 100 by 100 hysterons more or less, and then I put the values of the resistance values and the magnetization values from the curves that I show. So that's kind of the only parameters that I use. And the other important parameter here, I was too fast, then I didn't explain, but here, wait. So this alpha here is the ferromagnetic phase fraction. Typically, this ferromagnetic phase fraction doesn't depend on the history of the temperature. But here, what I did was to introduce like a cutoff. So it's basically putting into the model the fact that if you go to a certain temperature, when you reverse, you don't get the whole, so not all of the domains reverse back. And that is the trick to actually reproduce these whole curves. So the fact that this curve here follows the magnetization and this one here follows the resistance is using only those two parameters.
Are there any other questions?
To understand this space fractional ferromagnetic and antiferromagnetic parts can be like seen on experimental view, on the experimental view.
Yes, so the percolation, the phase fraction can be, so yes, if you do, for instance, an experiment of, let's say AFM. AFM is atomic force microscopy. So it's basically a tip that is very small in size atomically, and then you scan the sample at low temperature, and then you put a tiny current into the tip, and then you can measure locally the resistance. So you can map by atomic scale the local resistance. And typically you see that for particular configuration, you see a path always that crosses. You see most of the domains that are connected. That's one thing. It's more tricky to measure the percolation threshold in the magnetic domain, let's say. So for that, you have to use a magnetic tip, but that doesn't work sometimes very well. So for that, it's kind of complicated. I mean, there is something equivalent to the local resistance, which is MFM, which is magnetic force microscopy. And then, but I haven't seen works on doing that with percolation things. But yes, it's possible to actually see this. Yes, we have done that in some other systems, but for this particular one, we haven't. Yeah, so the praseodymium there is there because it has a smaller ion size, so it introduced more disorder into the lattice. And as you were asking, so disorder plays a role, and then you need some degree of disorder to be able to connect all these domains that will grow. So you need basically that is called like nucleation sites. Thank you. Yeah, that's kind of the word in this context.
Questions?
Yeah, okay, thank you. Sí.
Da igual. Listo. Ah, listo. Perfecto.
Okay, so let's welcome our next speaker. And his name is Andrés Rosales Rivera. And he's going to talk about from ferromagnetic to spin gas behavior and back in laminar manganese oxide window and So,
Muchas gracias.
gracias.
Buenos días de nuevo. Primero que todo, la presentación la voy a hacer en español. Por favor, agradezco mucho su comprensión. Muchas gracias a Gabriel, a José Daniel y a mi querido profesor Alejandro por su invitación. En esta presentación voy a revisitar una antigua, bastante antigua controversia de hace más de 100 años. Entonces, es un tema que va a indicar que un sistema ferrimagnético normalmente lo que se considera es que está formado por dos subredes, así como un sistema antiferromagnético. Sin embargo, hay posibilidad de que los sistemas ferrimagnéticos frustrados sean constituidos por más de dos subredes. Eso puede en este momento reconciliar una antigua controversia que surgió acerca del concepto del magnetón de Weiss, que fue introducido por Weiss por el 1907, fue bastante debatido y hasta 1940 Neil dice que la interpretación que Weiss le da a una cierta medida no es correcta e introduce el concepto de ferrimagnetismo. Bien, ese es el mensaje principal. Yo vengo de la ciudad de Manizales, es una ciudad de bellos paisajes, es la ciudad carretera de Colombia por excelencia, queda al norte occidente de Bogotá. Ese trabajo hecho en colaboración con los profesores Oscar Giraldo, el líder de la parte de la síntesis de los materiales con los que ustedes van a presentar, Mónica Gómez, estudiante de su época de doctorado, Naida, también colabora ahora, y el profesor Diego Murata de la Universidad de Campinas de Brasil, con quien nos colaboró con la medida de manifiesto y algunas otras conversaciones. El plan es muy rápido, es entonces revisitar el concepto de magnetón de Weiss, una controversia, y mirar cómo posiblemente se puede superar esa controversia. Un poco la introducción, motivación sobre la importancia de trabajar en estos óxidos de manganeso que son formados en láminas. ¿Sí? Sobre la síntesis y caracterización voy a pasar muy rápido y para dedicarme completamente a la parte magnética. Sin embargo, es importante aclarar que esta caracterización estructural, química y térmica es fundamental para la descripción y entendimiento de la parte magnética. Estos materiales han sido bastante trabajados en la parte eléctrica, en la parte estructural. Sin embargo, con respecto a la parte magnética, hay muy pocos trabajos. Los resultados, discusión e interpretación, un resumen, comentarios con las conclusiones y de pronto algunas perspectivas. Entonces, como comentaba, surge al siglo XX, una controversia por la interpretación de esta curva que es la inversa de la susceptibilidad en función de la temperatura para su época en manganitas. Entonces, Weiss encontró que esa curva aparentemente se daba en trazos. Esta parte en trazos lineales, esta parte lineal, esta parte lineal. Entonces, a partir de él, y basándose en las ecuaciones presentes del momento, entonces él usa la ley de Curie y también un resultado de Langevin, en el cual establece entonces que una cierta cantidad denominada mu, que es proporcional a la constante que aparece en la ecuación de Curie. A partir de él, de esos dos conceptos o esos dos resultados, él entonces haya el valor de la pendiente y la relaciona con, aparentemente, con un magnetón que se denominó magnetón de Weiss, porque encontró que en esta parte de acá la pendiente va cambiando, pero entonces encuentra resultados que son aparentemente múltiplos o son múltiplos de una cierta cantidad a la cual le llamó magnetón de Weiss. Esa historia fue superada y hoy en día olvidada. Sin embargo, pues tuve la necesidad de comenzar a hacer un poco de historia para poder como entender los resultados que estamos obteniendo desde el punto de vista magnético. Sí. Hasta esa controversia duró hasta la década del 40, cuando Neil introduce que realmente esta curva es una curva continua, suave, y introduce entonces el concepto de ferromagnetismo para un sistema de dos redes y lanza su ecuación del inverso de la susceptibilidad. Ahí aparentemente la controversia termina. Sin embargo, en el decorrer de los tiempos, en un trabajo del año 2000 por el profesor Jairo López de Almeida, profesor de Brasil, él en sus trabajos teóricos indica que un sistema antiferromagnético altamente frustrado puede ser constituido por más de dos subredes. Entonces, con base en eso, estamos haciendo nuestra interpretación de los datos. Sobre los materiales, como comenté, esto es un óxido de manganeso, son formados su núcleo por octaedros. Esta es una lámina, esta otra lámina, y esta lámina de acá es normalmente constituida por átomos. Los óxidos del manganeso tienen una alta complejidad, son muy interesantes, y la alta complejidad viene del hecho de que el manganeso puede tener varios estados de valencia, ¿sí? Y eso le da una complejidad, una riqueza, pero totalmente compleja. Y estos materiales se han trabajado bastante para varias aplicaciones, principalmente para baterías recargables y convencionales. Sobre la síntesis, aquí entonces, a través de los elementos o análisis de química, se ha determinado la relación de cobalto manganeso. Inicialmente tenemos el sistema óxido de manganeso y después se va dopando con cobalto. Ahí está la relación y los nombres correspondientes. Tenemos resultados de dirección de rayos X en los cuales nos indica que la fase principal es una fase constituida por pildecita. Sin embargo, cuando le va colocando el cobalto, pueden surgir otras fases secundarias como la ruinequita y finalmente un tipo de espinela. Aquí es solamente para tomar un sistema de referencia, es un óxido de manganeso basado con magnesio. Aquí es el magnesio, aquí entonces sin cobalto, aquí es una primera inclusión de cobalto, y así sucesivamente. La mayor cantidad de cobalto es para la muestra que es denominado horizontal. Aquí está, es muy importante para nosotros porque a partir de esto, el contenido de esta tabla, lo que más interesa en el momento, pues tenemos en cuenta estas relaciones molares entre esas cantidades de elementos o de iones, en el caso particular de cobalto y manganeso, que está oxidación manganeso. Entonces, cuando tenemos para la muestra de magnesio solamente un cobalto, el estado de oxidación es completamente 23, lo teórico es 4, entonces es el más alto de este conjunto de materiales. A medida que comenzamos a dopar el material con cobalto, entonces como vemos, comienza a disminuir levemente. Pero eso va a significar la inclusión de cobalto que le va a dar una riqueza y una complejidad al sistema. Aquí están otros cálculos, se ha mirado la fórmula estructural del sistema. Y ya propiamente lo que podemos pensar que está sucediendo es lo siguiente. Basado en esos elementos, entonces nosotros podemos considerar que el sistema está formado por Mn3+, y Mn4 más. Entonces hay un exceso de concentración de Mn4 con respecto a Mn3. Y mirando el spin de cada uno de ellos, se forma entonces como un exceso de concentración de Mn4, se forma lo que es el estado ferrimagnético. A partir de que entonces comenzamos a adoptar el sistema, entonces comienza a introducirse un poco de cobalto que se va a ocupar parte de los sitios octaédricos donde está el manganeso 4. Al ir aumentando la cantidad de cobalto, llegará un momento en el cual ya no se puede ir al sitio del Mn4 y entonces el cobalto irá al sitio del Mn3. Eso lo que va a introducir es una serie de interacciones que son competitivas. Propiamente para la parte magnética, aquí tenemos los resultados de magnetización de temperatura para diferentes muestras. Entonces, aquí podemos ir observando cómo va cambiando. Me detengo bastante en esta parte. Entonces, aquí tenemos medidas de susceptibilidad realizadas con el grupo del profesor Fernando Machado de Brasil. Y este es a campo cero. Encontramos aquí este máximo que indica la temperatura de transición. La forma de esta curva, el experimento lo hemos hecho siguiendo la ruta de cero field pooling y field pooling. Esta corresponde a, y la cual no voy a detallar más, a la respuesta de cero field pooling. Esta es una forma característica de un sistema ferrimagnético como vamos a soportar en las siguientes transparencias. Este es para la muestra que domina OL1 un poco alto y está sin dopar con cobalto. Y miren que la forma de la curva va cambiando fuertemente. Esta tenemos un poco más de cobalto y este es el resultado que nos dio aparentemente una curva sin mayor gracia, pero de cuanto la más interesante porque les voy a presentar y ver que esta tiene un comportamiento parecido a un vidrio de spin. A medida que seguimos aumentando la cantidad de cobalto, la respuesta en magnetización va cambiando nuevamente. Aquí lo tenemos de esta manera y tenemos un máximo inicial y aquí un pequeño onzo. Seguimos aumentando la cantidad de cobalto y pareciera que el sistema va recuperando la forma inicial cuando el sistema está sin tanto cantidad de cobalto. Pero aquí vuelve nuevamente a suceder la cuestión del máximo o un tipo de hongo allí. Para analizar mejor esas medidas, entonces hemos hecho inverso la susceptibilidad y uno ve que para esta muestra sin magnesio hemos eliminado OL, esta es la respuesta de esa parte, la que más me interesa la zona pública. Esta es una curva que hemos ajustado con la ecuación de Nil y ajusta muy bien. Y entonces, esta es gobernada por esa ecuación. De ahí encontramos que esta temperatura paramagnética vale 29,84. La comparamos con la temperatura obtenida por medidas de subjetividad C y miren la concordancia que hay entre los dos sistemas, entre las dos medidas. El uno me da 29,84 y la otra me da 30 grados centígrados. Esta es supremamente interesante. Y entonces podemos comparar este gráfico. Este gráfico aquí tiene entonces esta primera parte que aquí, la podemos hacer de esa forma. Hemos hecho los cálculos usando la ecuación de Nil y casa perfectamente. Para este tramo es lo mismo. Entonces, esta sería una primera subred y esta da la idea de otra subred ferrimagnética. Entonces, esta curva es bastante parecida con esta curva de acá. Seguimos haciendo ese procedimiento y nuevamente la susceptibilidad va cambiando. Un momento interesante aparece cuando entonces hace la derivada de la susceptibilidad definida como la magnetización sobre el campo magnético. Aquí las medidas son para 1 kHz y aquí vemos cómo va cambiando completamente esa subjetividad. Me detengo en esta parte. Entonces, este es un material típico ferrimagnético. Aquí va introduciendo, miremos que aquí tiene dos mínimos, y aquí tiene una serie de mínimos, no hay solamente un mínimo. Esta curva que aquí es muy similar a la de un vidrio de espino y se puede justificar porque la derivada de la susceptibilidad lo que da reflejo que la fluctuación de la magnetización de una medida de calor específico, ¿sí? Pero verifica en otra muestra cómo es el comportamiento del sistema. Entonces miremos que a medida que vamos cambiando, la condición del cobalto va cambiando completamente el panorama de la susceptibilidad. Hasta llegar una curva muy similar a la inicial. ¿Sí? Aquí vamos de un comportamiento ferrimagnético a un comportamiento vidrio de spin y después vamos recuperando nuevamente el comportamiento ferrimagnético. Aquí sería ferrimagnético de dos subredes, este sería de más de dos subredes. Y finalmente llegamos a un comportamiento ferrimagnético de más de dos subredes, esas dos subredes, pero con el mínimo que aquí, no solamente un mínimo, aquí otro mínimo, pero este mínimo de estas ya por clúster de spins. Me detengo fuertemente en esta para comparar la respuesta de la susceptibilidad con la capacidad calorífica. Entonces uno observa que la capacidad calorífica a campo constante es para 1 kHz, tiene una pequeña anomalía por acá. ¿Sí? Y entonces uno observa que esa temperatura, esa pequeña anomalía, coincide bastante bien con la temperatura de el mínimo obtenido por la derivada de la susceptibilidad. Para entenderlo, entonces, usamos diferentes ecuaciones. Esta ecuación es una ecuación planteada por Fischer sobre la K de 60, en la cual está relacionando la derivada de la susceptibilidad con la capacidad calorífica. Aquí la magnetización en términos de unidad de correlación, y aquí la susceptibilidad en términos de la derivada de M en función de tiempo. Un resumen que acá voy a pasar esto y lo encontramos acá. Entonces, inicialmente el sistema es sin dopar. Aquí esto está la estructura, esto me está representando los átomos de oxígeno y el átomo de manganeso Mn3 el que está allí en el centro. A medida que vamos dopando el sistema, entonces va poniendo la relación cobalto-manganeso, pero eso hace que las interacciones que existen en el sistema inicialmente en términos de superintercambio y doble intercambio, la una es la superintercambio más de naturaleza antiferromagnética y la otra intercambio ferromagnético. Entonces las interacciones van compitiendo entre ellas y es posible que esa competición de lo que esté dando lugar a el sistema medio extinto. Pero a medida que aumentamos la cantidad de cobalto, la relación ya va cambiando y va predominando hasta que finalmente encontremos nuevamente el estado ferrimagnético. Entonces el resumen sería ferrimagnético dos subredes, ferrimagnético de más dos subredes, vidrio de spin, tipo vidrio de spin, pues en canónico nos faltan todas medidas para caracterizarlo, y ferrimagnético de dos subredes para algunos clústeres de spin que se deben formar. La posible reconciliación entre las medidas que observó Neil y Weiss. Entonces, muy probablemente, con base en este trabajo, podemos ver que las medidas que tenía eran correctas. Lo que no era correcto es la interpretación de las medidas. Pero el resultado experimental como tal era correcto. Y adicionalmente a eso, lo que sucede con la teoría de Neil sobre el ferrimagnetismo es que se puede ampliar a más de dos subredes. Ese sería el mensaje. Muchas gracias por su atención. Y hola un poquitico aquí, unos que están viendo más para un próximo evento que estamos pensando en En Manizales, aquí está entonces algunos paisajes de Manizales. ¿Sí? Bueno, esto es básicamente la cuestioncita. Entonces, con mucho gusto.
Yo para una pregunta súper corta. We have time for a very, very small question, very short question. Okay, thank you very much.
Gracias.
Okay, our next speaker is Professor Paula Hidalgo, of the Universidad de Los Ángeles.
Hay algunos que no.
Okay, so Paula is going to talk about defect-induced ferroic states in solid solution of layered van der Waals.
Materials.
Bueno, muchísimas gracias. Thank you very much to the organizers for the invitation to this workshop. So I want to share with you some of the results we have been developing in our group in the recent years about defect-induced ferroic states in transition metal bicalcogenate specifically, which is a type of layer van der Waals material. The work I'm gonna be presenting today is summarizing these two publications in case someone wants to follow up on the topic. There we go. So the spirit of what we are doing right now to promote and discover these ferroic states in these systems is to create solid solutions of two original materials following some guiding principle that we have in strongly correlated system, which is mixing two systems that have originally two different electronic states, and creating solid solution could promote the existence of both ferroic states at the same time in one material, which can actually give a lot of opportunities for new applications of the use of these ferroic states in this compound. So we will start with a ferroic or ferromagnetic semiconductor, we call it, which can be ferroic or it cannot, depending on the defect structure that has in its own. And we will start also on the other side with a ferroelectric metal. These two concepts are actually very rare. Having a ferroelectric metal, it's actually not a common thing to say in solid state. And we mix it and create these solid solutions, which are single crystals that contain all the mixture of these elements in their structure. But on top of that, they have defects, which are actually configured through this delta parameter, which measures the amount of the percentage of defect that this material has. Through this, we have observed that we can promote multiferroid state, which is the simultaneous presence of different ferroid states in these materials. And the beautiful work of my students in the group, in which we have been focusing on two main systems, the mixture of tungsten diselenide and tungsten disulfide with tungsten ditelluride, generates these beautiful phase diagrams, which shows the behavior of the different ferroid states, in which, depending on the composition, the relative composition of selenium, tellurium, and the amount of defects on the material, we can have multiferroicity in a big portion of the phase diagram, or just a paraelectric material with ferromagnetism, which will be this one, or vice versa. We can have all the mixtures of these different ferroic states. So I'm going to show you a little bit about how we get there. And so we have layer van der Waals materials, which are materials that can span a different, like all the different ranges of electronic properties that we can think of. The most famous of them is graphene, and many people work on this. And in the last 20 years or so, there have been big efforts in the study of the transition metal bichalcogenates, which are in this corner. So these materials are layered van der Waals material because within a plane, the materials are held, the atoms are held by covalent bonds, and in between planes, they are coupled with van der Waals interaction. So this gives the possibility of actually we can exfoliate these materials, and we do so in the laboratory to a single monolayer of this compound and to study the properties in this limit. So we can peel off these layers and obtain one slab of this compound. So these materials are very interesting because within the transition metal bichalcogenates, we can have semiconducting compounds. We have multiple applications in terms of optics and many others, and metallic compounds with, for example, superconductive properties, charge density wave things, effects that are very, very interesting. So we are mixing them, and we are obtaining these solid solutions. It turns out that these solid solutions we have found that actually enhance the ferroid properties that could be originally in the parent compounds, and on top of that, it can promote the presence of multiple ferroid orders at the same time. Okay, so I guess you know what ferroid orders are, but there are some that are less common than others. For example, we have ferromagnetism, which you guys have been talking throughout the morning. But we also have ferroelectricity, which is the ordering of electric dipoles that we can have in the material that can interact with each other and point in the same direction below certain temperature. We can also have a less common one, which is ferroelasticity, in which domain elongate along a specific direction and order as a result of its coupling to strength. These ferroid orders are very useful for different applications, for example, to create non-volatile memories. And this is a characteristic curve of polarization versus voltage for a prototypical ferroelectric that actually we measure it in the lab through current voltage curves. This is the prototypical shape of the current voltage curve, which I'm going to appeal later on the talk. So we can actually create ferroelectric ramps, not storing the data in the magnetic polarization, but on the electric polarization. So these are new generation memories. Interestingly, if we have multiferroids, and particularly the multiferroid that couple ferroelectric order with ferromagnetic order, we can have magnetoelectric multiferroids. And there are multiple applications envisaged around these kinds of materials that are very interesting. Like, for example, some spin valves in which we can control the magnetic state, not with magnetic field, but with electric fields. So this is very interesting. So why studying van der Waals materials? So most of the multiferroids that we have available right now are three-dimensional materials. And they suffer from depolarization once you cross some length scale when you nanostructure these compounds. The materials depolarize due to quantum fluctuations or other effects. So there is a big interest in studying ferroid orders in low-dimensional systems. So just for the spirit of in understanding the physics of what generates long-range order in low-dimensional physics, this problem is interesting. And we are not the first in studying ferroid orders in these van der Waals materials. As you can see here, there is a lot of research going on around hysteresis loops that have been measured in multiple TMT systems, transition metal bichalcogenates, in which we observe that there are common features in the observations of these ferromagnetic loops, focusing on the ferromagnetic sets. For example, if we have a sample that is very slightly magnetic, almost paramagnetic, like you see here for molybdenum disulfide, we can actually enhance the magnetism through proton irradiation. So creating defects in the system is beneficial for the ferromagnetic states. So that's one key component for the magnetism. In this system, for example, promoting a particular polytype or crystalline structure for this material is also beneficial for the ferromagnetism. So the crystalline environment, and we all know that's very important for creating magnetic moments, promotes also the formation of the strengthening of this magnetism. And dopants. So these are some magnetoresistant hysteresis curves, which the hysteresis evidence the ferromagnetic states. And this has appeared in this compound, the tungsten diselenide. I'm going to explain later today. It's the one that we have been working through the doping of vanadium. So these three key components are key components for promoting these ferromagnetic states. So let's see, on the other hand, what has been done in the ferroelectricity. So the ferroelectricity in this material is revealed through the measurement of piezoelectricity. So it turns out that all ferroelectrics that are here are also piezoelectrics. Piezoelectrics are materials that respond and deform in response to an electric field or a voltage. So through measuring how the material deforms with an electric field or a voltage, we can actually evidence the presence of the ferroelectric states. So we can come with a tip of an AFM and touch the sample, scan the sample, put a voltage, and see what's the deformation through the deformation of the tip. And this technique is called PFM, and we have been doing these kinds of measurements. These are not ours, this is other group. And in the transition method, by chalcogenides, the presence of ferroelectric states have been reported as hysteresis loops in some particular signal of this PFM signal, which actually evidence that there is a hysteretical behavior of the polar domains in the material. So these observations have been done, this hysteresis observed, and although this says that it's in the bulk, this is a bulk that is nanostructure, meaning it's not a bulk macroscopic crystal, but it's a crystal that has been thinned down in order to do these kinds of measurements. More commonly, these piezoelectric and ferroelectric effects have been reported in, for example, nanolayers and monolayers of this, for example, tungsten diselenide. And it turns out that we can measure the amplitude of deformation as a function of a voltage and define a piezoelectric coefficient, which is that response of the material through deformation of an electric field. This behavior is not hysteretical, it's only piezoelectric, so the material is not ferroelectric, but it talks about the formation of some polar domains in the material. And this behavior and this big response to this deformation happens only in an odd number of layers of the material, which is, I think the battery is out. Okay. So, and this is an effect that is caused because in an odd number of layers, the crystal structure is non-centrosymmetric, which seems to be a key component for the ferroelectricity for these materials. But this only happens in the nanostructure. So what we have been doing is that we are trying to promote the presence of these ferroic traits through these solid solutions. So the creation of this solid solution has all these three components that I talked to you about in terms of the ferromagnetism. It promotes locally, and has been reported that it promotes a 1T local structure around defects. It promotes the formation of defects because of natural processes of the chemistry of the growth of the crystals that we have in the lab, and it has dopants as well by substitution of these atoms. So what we have done is, by combining these compounds, we have not only strengthening the ferroelectric and ferromagnetic states in these materials, but we have also created multiferroicity in this family of compounds. And so far, we have the first report of multiferroicity at room temperature for this family of materials. So what we do is that we go to the lab, we grow beautiful single crystals, we measure its chemical composition, and that way we can determine the amount of doping that we have and the amount of defects that we have. And through carefully studying what's and this is the crystal structure that we have, we know that the atom B substitute atom A by incorporating into the sites specific for this atom. But we can also have defects in the material. The most common types of defects are vacancies, which is a site that is not occupied, but we can also have interstitial defects. How do we know that these are the defects? Because they have the lowest formation energy. So these are the most likely defects that we can have. We have studied these specific mixtures of these compounds, and I'm going to go really fast because time is almost up. So we summarize our results in this phase diagram. So we plot here the amount of selenium relative to tungsten and the amount of tellurium relative to tungsten in this specific mixture. The stoichiometric compound with no defect have this formula, which we can represent in this diagram in this line. So the compound with no defects at all, with just replacing selenium by tellurium, goes under this line. As we increase X, the amount of tellurium in the compound, we move toward that region in this line, and different amount of defects can be represented by parallel lines like this in this phase diagram. And delta increases in this direction. So in that way, we can represent in our phase diagram a region in which we have vacancies at the dominant defect, interstitial for delta negative and vacancies for delta positive. What we have done is that we have actually grown all these different materials. This one over here that with open symbols are the one reported into the literature in which the role of defects have not been considered at all. But we know that the defects are important, and we have taken track of this amount of defects, and we have grown all these different compounds that we show here. For all these compounds, we study their ferroic properties. So we see that with a low number of defects, we have paramagnetic states, and the paramagnetic state starts to develop into little hysteresis that speaks of ferromagnetism. And then we have big hysteresis loops, which talks about the strengthening of this ferromagnetism for the region of the phase diagram in which we have lots of vacancies in the system. So we characterize this magnetic phase by the coercive field. So this is the field at which we can switch the magnetization direction. And we can see that this coercive field scales with the amount of defects, sorry for the resolution, but as the amount of defects in the material grow, the coercive field also grows, which does not correlate very well with the amount of tellurium in the system. All right, so we have a first preliminary conclusion, and it's that the vacancy, the amount of defects that we have in the system, and particularly vacancies, are very good for promoting ferromagnetism, is the driver for this state. How can we explain that? If we have defects in the system of the vacancies of the chalcogen atoms, the tungsten ions are not surrounded by many chalcogens. This promotes the localization of the d electrons in this tungsten, creating magnetic moments. And we have actually confirmed this through DFT models. So this tungsten that is over here is this one over here, in which the arrow represents the amount of magnetism for that atom. And this one too, these two here are here. We have also simulated some realization in which do not have many tungsten ions surrounded by vacancies, and those realizations are not magnetic. So this actually speaks of the importance of vacancies in this system. We have done exactly the same for the ferromagnetic or ferroelectric order, and I'll go really, really fast here. So we have very good piezoelectric materials with piezoelectric coefficients that are comparable to commercial piezoelectrics like lithium niobate or others. So that's actually very nice, promoting these high values that are useful for engineering applications. And we have seen hysteresis, beautiful hysteresis loop in these piezoelectric measurements that speaks of the ferroelectric ferroelectric order. So let me go really fast here to summarize these results. So Harold Rojas, who is my PhD student, has done a fantastic job at summarizing all these results. So we have identified in which places of this phase diagram, this compositional phase diagram, we have ferromagnetism, ferroelectricity, and multiferroicity. And by doing so, we have summarized our results in this beautiful phase diagram in which in this blue region, we have multiferricity in a two-dimensional system. Just as a propaganda, I will tell you that we have other systems that show very similar behavior, in which we have very similar phase diagrams that show ferromagnetism and ferroelectricity, evidence in IV curve with some ferroelectric characteristics proper of ferroelectrics in this compound. And all these properties are in the bulk. But we are also moving toward characterizing these states in the nanostructures that we can form. So in our lab, we have ways of peeling off these crystals and depositing these crystals in electrodes. These are some gold electrodes. We measure IV curves or current voltage curves. In this here, over here, you can see a monolayer of tungsten disulfide doped with tellurium, and we see beautiful ferroelectric curves, very similar to this one, but with variations in the parameters. So with that, I would like to conclude acknowledging my group. 70% of our group are working in similar projects around these heroic states in these two-dimensional compounds, but special thanks to Harold, Ramon, and Valentina, who have put a lot of effort into preparing all the results that I'm showing you here, and our collaborators in different institutions in Colombia and our funding. Thank you very much.
Okay, we have time for initial questions or no? Are there any questions?
So the effects are more efficient to increase ferroelectricity than putting more selenium. Yeah.
Tellurium.
Yeah.
So our calculation through our collaborators show that once you create a vacancy, that creates a dipole moment, in a local dipole moment. But if that vacancy or that structure has tellurium in its structure, that dipole moment is 10 times bigger.
Okay.
So you can have dipoles even with the selenium
Alone.
material toward the selenium, but the tellurium, because of stronger spin orbit and all other effects, can actually enhance that electric dipole moment that you have.
Okay.
But you need to have both components, vacancies plus tellurium, in order to have a ferroelectric state.
Okay. Thank you.
Thanks. I just have one small question. Is there a way to ensure that you will have the vacancies in the compound during the preparation process, or?
There are many interpretations to your question. I'm going to try to answer it in different perspectives.
Okay.
So the first one is that we are working towards having a direct observation of the vacancies in the system. What we have done is like macroscopic experiment, and through an analysis of the hierarchy of the energies of formation, we have deduced that we actually have vacancies in the material, and that makes sense. But we do not have still a direct observation of vacancies in the structure, which we would have to do electron microscopy in order to observe that directly. So we are working toward that. And the second one, I forgot the second interpretation that I was going to give.
Don't worry. Yeah, that was. Thank you.
Thanks.
Like how I. Figure the família. Change dynamics on complex hard politics that was related circulation flow.
Yes.
Hello, everyone. My name is Liliana Gomez, and today I'm going to talk about string dynamics of complex topologies from a bond-correlated percolation approach. This is a joint work with Professor Gabriel Pérez and Fernando Gomez. So let's start with the motivation. So basically, quantum annealing is a class of quantum computing that aims to exploit quantum advantage to explore more efficiently energy landscapes and also to escape local minima. So during this workshop, we have seen why this is important because energy landscapes are a hard problem that we are trying right now to solve. And well, quantum annealing is a really promising option for doing so. So as I was telling you, the main idea is to map hard combinatorial optimization problems onto spin glass Hamiltonians. However, and this is a crucial point, that cannot be implemented on an arbitrary graph. Indeed, those problems should be embedded into these topologies. Well, these are an example. These are the D-wave topologies, which are the Chimera, Pegasus, and Zephyr graphs. Each one is the iteration of the previous one in this order, which means that the Zephyr one is the most densest of the most with the most uniform connectivity. So basically, these kind of topologies are carefully engineered and designed in order to optimize qubit coherence and scalability and many other factors that are relevant when we're talking about quantum technologies. So as I was telling you, one needs to embed the problems that it's trying to solve with the spin glass Hamiltonians onto those topologies. So that, of course, opens a big question, which is how does hardware connectivity shape the energy landscape and the relaxation dynamics at finite temperature? So just to clarify, in the quantum machines, in physical devices, each of the nodes represent a qubit. For example, D-wave uses superconducting flux qubits, and the edges correspond to the interactions of the ensemble in the machine. Now, studying these kind of topologies from a statistical physics perspective is really challenging. There are several studies that have suggested that there is no spin glass phase in this kind of topologies, which makes their phase space rather simple. And that's not what we want because we need to solve hard problems using this machine in order to assess quantum advantage. If we're testing them with simple problems, then we're not really measuring what we want. So, studying these networks, there's an ongoing debate if they are really good candidates for doing quantum annealing. And that's mostly because they have been studied from a finite size scaling perspective using binder count cumulants and also the spin overlap parameter, which may not be the best option in this kind of topologies that, as you saw on the previous slide, are non-translational invariant and well, they're really interconnected and are subject to dimensional graphs. So during this work, we tried a different approach. We tried a bond-correlated percolation approach based on the connected plane clusters. So the connected plane formalism is a direct mapping between the ferromagnetic Ising model and a bond-correlated percolation model that in the ferromagnetic case works really well. It is really interesting because it allows one to analyze or to interpret the thermodynamic correlations from a geometrical perspective in which the group of clusters correspond to the groups of correlated spins. So it's really useful and really interesting also because the point at which the giant cluster appears, or the point at which the cluster percolates, it's the same point of the critical point. So that's where the direct mapping is. However, we're working with the spin glasses. In particular, we work with Edwards Anderson spin glass
which means that the coupling parameters between spins are drawn from a Gaussian distribution between 0 and sigma 1. So here things get more complicated. That direct mapping no longer holds, because as you can see in this figure, there may be two spins that are connected through paths that have opposite signs, which means that at the end of the day, they will cancel. So the paths between spins no longer represent thermodynamic correlations. However, and this is really interesting and where the main physics is that those bonds defined according to this probability rule, that's slightly modified in order to just make bonds. If they're anti-parallel, they're connected if the coupling parameter is less than 0. And if they're parallel, they're connected if the coupling parameter is greater than 0. They cannot close a frustrated loop due to this definition. So they, in the cluster, there are not groups of spins that close frustrated loops, but connectivity remains non-negative and still percolates. And that happens at a temperature that we will call TP. So this will be important later on. Well, the key insight is that in TP, this TP is composed of bonds that are satisfied, which means that they can minimize the energy. But in that giant cluster, there may be spins that are in presence of frustration. So if you do a perturbation, if you want to rearrange your system, that propagation will propagate along that cluster of connected spins, that giant cluster if you are below TP, and it must navigate regions with frustration, which means that the propagation must navigate frustration, and that will lead to slow dynamics and corrective dynamics. That's like the characteristic of a spin glass phase, or not a spin glass phase, but a frustrated dynamics, and it's a sign of a rugged energy landscape with many local minima. And that's what I'm showing here. This is the particular example for a 3D network in which it has been shown numerically that there is a spin glass phase. So in the spin glass phase, the energy landscape is really rugged. There are many local minima, as you can see here, and the spin is still autocorrelation with decay following a power law. Meanwhile, in the non-exponential regime, that's the one that's defined by TP and TC, I'll explain it later. The decay of the spin autocorrelations follow a stretch exponential with a beta parameter, but there's also the paramagnetic phase in which the spin autocorrelation just follow a simple exponential decay. So what we're trying to understand with this work is this regime of non-exponential relaxation, because it can be identified with the percolation formalism that I just showed you. But here is also important to notice that there may appear another temperature scale related to the disorder on the spin glass, because we're working with an Edwards-Anderson distribution, which means that the coupling parameters are random, so that also induces non-exponential relaxation. So this regime is both due to frustration and disorder, but what's interesting here is that if you have a fully frustrated model in which there is no disorder in the coupling parameters, the only temperature scale relevant for that non-exponential relaxation is Cp. And that's the one that we try to study. So what's really useful for you to use in a percolation formula is that we can use observables from that mathematical frameworks, such as the spanning probability and the average path length. So we measure both of them. And in particular, we weighted the average path length with the inverse of the coupling parameter with the magnitude. That spins which have a bigger coupling parameter are taking us closer. And we also measure the spin autocorrelation using a simple dynamic, just a classical Monte Carlo with single spinning flips. And here you can see like the sizes we use. Of course, these are not as big as we wanted because these networks are difficult to simulate, but we also decided to work with these networks, with these sizes, because those are the ones that are used in big ways. So this gave us better insights. And well, we did a comparison with the 3D network, but as I said from the beginning, it has been shown that it has a spin glass phase. And these are our results. Notably, the superior network, the most interconnected one, has the higher TP. But what's really interesting is that the average path length tell us a lot of information that we couldn't see before. For instance, the Chimera network, the orange one, it has the highest average path length in magnitude, even though it has the lowest TP, which means that it has a lot of bottlenecks. Its topology is composed of spar interconnected cells. So yeah, this gives us information about how frustration creates those paths according to the topology and the bottlenecks it encoders and, well, it's information that couldn't be obtained with the previous formalisms. And this is the relaxations dynamics. Here, the y-axis is risk-related. So if one has a stress exponential, the linear form, its slope will correspond to the beta parameter. So a simple exponential will be a linear form with slope 1. And that's what's actually being shown with the red dashed line. And the blue dashed line shows a power law behavior. So as you can see here, all of the topologies are, well, their relaxation is pretty similar. Of course, that it's escalated according to the temperatures intrinsic to each topology, but the behavior is pretty similar. So even though it has not been shown numerically that the Chimera, Pegasus, or the Telegraph have a spin glass phase transition, their relaxation dynamic is pretty similar to the 3D one, in which there has been shown. And well, basically all of the blue colors corresponds to temperatures below TP and the red ones to temperatures above TP. And yeah, just to summarize a bit about the physical interpretation of what's really happening. Here, as I said, at the beginning, TP corresponds, well, TP, below TP, there's this giant cluster in which all the bonds are satisfied. And this means that the spins that are frustrated, that are in frustrated regions, their effect will propagate across the whole lattice through those satisfied bonds. But below TP, that giant cluster fragments, so there's no longer this low collective dynamics due to the multiple relaxation scales and environments which the correlations must navigate. So yeah, and what's interesting, well, it's not a big surprise, but TP is topology dependent and it serves as a connectivity result metric for hardware resilient thermal effects. And yeah, well, basically, this can work to better design hardware topologies. And also, it's like another perspective in order to understand that maybe the numerical methods that we're using for identifying spin glass phases in these topologies are not as useful as we previously thought, and that the phase space is most complex than what we thought, and that this percolation approach that at the beginning, well, seems to fail when understanding frustrated models can have other applications, such as the one I present. And that's all.
So what sort of behavior do you see if you make the same analysis on a 2D Edward Anderson model? Because we know there's no spin glass transition, and you should, I guess, be able to see similar things as you do in these complex topologies.
So it also has
And you know if anyone or you have made this path length analysis? Okay, thank you.
Yeah, so who showed and how that the spin glass temperature 0 for these geometries? Yeah.
Yeah, they use the replica parameter and they try to calculate the inner cumulants, but when they try to find the intersection through the curves, they didn't intersect, so they conclude there's no phase transition of the environment. Are there any more questions?
Yeah.
Well, I have a question. If you have a longer path when you show the results, it means it has a good topology or a bad topology. What's its relation if it's ordered or not?
The lattice, and if you remove one of those real particles, for instance, the ones that are between the intercells, then it was red. Bonds, that's also why the middle one has the lowest. But also
Thank you.
Are there any more questions? Okay, so let's thank Viviana. Now it's lunchtime, so we need to get into same room.
Sí, hagan para eso, sí, para que no se tenga que preparar y lo hagas de una vez ahí, y por si sale el
A ver, yo ya, pues, en realidad cuando sale algo lo estaba haciendo, cuando alguien se conecta, lo que nos complicaba. Entonces, al principio sí para poner la presentación en la
pues me dirás cuando
de pronto pues, para que presenten también. Sí,
y pues hablen yo también, profe. Yo, en mi caso, tengo control de para pasar si quieres, puedo hablar mañana.
sí, sí, pues,